For the vast majority of human existence, the Andromeda Galaxy remained a mere faint speck in the nocturnal sky. Some observers categorized it as a nebula, essentially a localized cloud of gas within our own Milky Way. Others, with bolder imaginations, speculated that it might indeed be a distinct galaxy in its own right. The eventual revelation of its true nature radically altered our comprehension of the cosmos. Andromeda is not simply another celestial body. It is the largest galaxy in our local group, a cosmic metropolis housing 1 trillion stars and countless enigmas. Furthermore, Andromeda represents our future within a grand cosmic waltz that unfolds over billions of years. Our galaxy and Andromeda are on an inevitable collision course, destined to coalesce into something entirely novel. What secrets does this galactic neighbor conceal? Could it harbor planets yet undiscovered? And could humanity, or some future creation, one day traverse the intergalactic chasm to reach it? A nebula or a galaxy? This was the crux of a 20th century scientific quandary. In the early 1900s, astronomers grappled with a question that would fundamentally redefine our understanding of the universe. Was the Andromeda Nebula merely another diffuse gas cloud within the confines of our Milky Way? Or was it an entirely separate stellar island, akin to our own but immeasurably distant? At that epoch, the universe, as understood by humanity, was considerably more circumscribed. The prevailing scientific consensus held that the Milky Way encompassed all celestial entities, every star, every planet, and every gaseous expanse. When telescopic observations revealed faint, luminous patches in the night sky, astronomers readily classified them as nebulae, presuming them to be interstellar gas clouds, possibly in the process of birthing new stars. Andromeda was one such enigmatic entity, a spirally shaped light source that stood apart from the myriad other nebulae catalogued in the heavens. The debate surrounding Andromeda's authentic identity intensified in the early 1900s. A contingent of astronomers posited that it was an independent stellar system, an island universe unto itself. This was a revolutionary concept. If Andromeda was indeed a galaxy, then the universe was vastly larger than anyone had previously conceived. It implied that the Milky Way was not unique, but rather one of an innumerable collection of galaxies scattered across the cosmos. A significant argument against Andromeda's status as a separate galaxy stemmed from the firmly held belief that the Milky Way was sufficiently immense to contain everything. In 1917, astronomer Harlow Shapley, after estimating the dimensions of the Milky Way, concluded its diameter to be approximately 300,000 light-years, an astronomical scale for that era. If Andromeda lay beyond the Milky Way, it would necessitate a distance of millions of light-years, a span that seemed almost inconceivable. Shapley and his adherents maintained that all known nebulae were integral components of our galaxy, rendering the notion of other galaxies superfluous. Countering this perspective was another esteemed astronomer, Heber Curtis. He drew attention to specific observations suggesting Andromeda's potential location far beyond the Milky Way. A pivotal piece of evidence was the presence of novae, stars that briefly flared with intense brilliance before fading. Curtis noted that novae observed in Andromeda appeared considerably dimmer than those documented within the Milky Way. Assuming these were analogous phenomena, the only logical deduction was that Andromeda resided at a far greater remove than previously assumed. Curtis also remarked upon Andromeda's intrinsic structure. It exhibited a spiral morphology, mirroring that of other enigmatic spiral nebulae observed in the sky. If these spirals were simply gas clouds within the Milky Way, their remarkably ordered configurations remained perplexing. However, if they were distinct galaxies, their spiral forms became far more comprehensible, vast congregations of stars, much like the Milky Way itself. This scientific schism culminated in 1920 at a momentous event known as the Great Debate. Shapley and Curtis publicly articulated their respective viewpoints at the Smithsonian Institution each presenting their evidence for and against Andromeda being a separate galaxy. Shapley championed the concept of a singular galactic universe, asserting that the Milky Way's sheer immensity obviated the need for other galaxies. Curtis, conversely, adamantly maintained that Andromeda and other spiral nebulae were independent stellar systems. The debate concluded without a decisive victor. Both individuals offered compelling arguments, and definitive proof was lacking to resolve the matter. Nevertheless, the quest for an answer persisted, and within a mere handful of years, the enigma of Andromeda would finally be unraveled. In 1924, Edwin Hubble achieved a monumental breakthrough, utilizing the 100-inch telescope at the Mount Wilson Observatory in California. Central to Hubble's investigation was a specific class of star known as Cepheid variables. These stars pulsate with a consistent rhythm, waxing and waning in brightness over time. Earlier in the century, astronomer Henrietta Swan Leavitt had conducted studies on Cepheids, uncovering a crucial correlation. The longer a Cepheid's pulsation period, the greater its intrinsic luminosity. This discovery implied that by measuring the rate of brightness variation in a Cepheid, astronomers could ascertain its true luminosity. Comparing this with its apparent brightness from Earth enabled them to compute its distance. When Hubble calculated the distance to Andromeda, the result was staggering. It was situated more than 2 million light-years away. This firmly placed Andromeda far beyond the Milky Way's boundaries, conclusively proving its status as a separate galaxy. Hubble's discovery revolutionized astronomy overnight. The Milky Way was no longer perceived as the entirety of the universe. It was merely one among countless galaxies, each containing billions of stars. The protracted debate that had spanned decades was finally settled. The concept of an island universe transitioned from mere theory to tangible reality. This revelation paved the way for even more profound discoveries. As telescopic capabilities advanced, astronomers identified an ever-increasing number of galaxies stretching across the universe, some vastly exceeding the Milky Way in size. The realization that our galaxy was but one of many sparked new inquiries into the universe's scale, structure, and origins. The field of cosmology experienced rapid expansion, moving beyond the localized study of the Milky Way to an exploration of the universe as a unified whole. Lingering doubts and unresolved early observations persisted. Even after Edwin Hubble's discoveries fundamentally reshaped astronomical understanding, uncertainties and unanswered questions lingered. The scientific progression is seldom linear, and the confirmation of Andromeda as a galaxy did not entirely dispel all ambiguity. Some astronomers were hesitant to fully embrace the revised cosmological model, and certain early observations appeared incongruous with the concept of multiple galaxies. A primary concern revolved around the luminosity of galaxies. If they were indeed millions of light-years distant, their intrinsic brightness had to be far greater than anticipated. Many scientists struggled to accept the notion that individual galaxies could radiate such immense brilliance across such prodigious distances. Explaining how these colossal structures generated such prodigious amounts of light posed a significant challenge, especially given that the energy generation processes within stars were not yet thoroughly understood. At the time, the prevailing theory regarding stellar energy production was still under debate. The concept of stars deriving their energy from nuclear fusion was not yet firmly established. In the early 20th century, a considerable number of scientists still subscribed to the belief that stars emitted light through gravitational contraction, a gradual compression under their own mass generating heat. However, this mechanism could not account for how stars maintained their luminosity for billions of years. If galaxies harbored billions of stars, as Hubble's findings suggested, a novel understanding of stellar energy generation was imperative to explain the emitted light. This issue was not resolved until the mid-20th century when researchers definitively established that stars are powered by nuclear fusion, transforming hydrogen into helium in a process that releases immense quantities of energy. Questions also arose regarding the distribution of galaxies. If the universe contained innumerable galaxies, why did they appear concentrated in specific regions while other areas seemed almost devoid of them? Certain celestial surveys indicated clustering patterns that were not immediately explicable. Early observations suggested that galaxies were not uniformly dispersed, but rather formed discernible groups and clusters. Some astronomers questioned whether this was an artifact of observational limitations, while others suspected it represented an intrinsic characteristic of galactic arrangement. If galaxies were congregating into groups, what force was responsible? Gravity seemed the most plausible explanation, yet scientists lacked the means to comprehensively study the large-scale movements of galaxies. Another source of doubt emerged from early attempts to measure galactic velocities. Hubble had demonstrated that galaxies were receding from us, but some astronomers encountered anomalous exceptions. A few galaxies exhibited minimal redshift, implying they were not moving away as rapidly as others. Even more curiously, Andromeda itself appeared to be advancing towards the Milky Way, rather than receding. If the universe was undergoing expansion, why was this immense galaxy on a trajectory of collision with our own? The eventual realization, understood by scientists much later, was that the overarching expansion of the universe did not preclude individual galaxies from possessing their own localized motions dictated by gravity. Andromeda and the Milky Way were sufficiently proximate for their mutual gravitational attraction to outweigh the cosmic expansion, drawing them together. Hubble had confirmed Andromeda's immense distance. But what of the numerous other spiral forms catalogued in the sky? Were they all as remote as Andromeda, or were some actually situated within the Milky Way? Astronomers were compelled to meticulously scrutinize each object to ascertain its true nature. In certain instances, what initially appeared to be a spiral nebula was later identified as something distinct, such as a planetary nebula or a supernova remnant within our own galaxy. The differentiation between galaxies and other celestial phenomena was not always readily apparent. If galaxies constituted colossal stellar assemblages, how did those stars originate? And did all galaxies generate stars at a uniform rate? Early observations indicated that some galaxies exhibited greater activity than others. However, the underlying causes remained poorly understood. Certain galaxies displayed luminous, glowing regions that seemed to signify vigorous star formation, while others appeared comparatively quiescent. Scientists required more extensive data to ascertain the factors driving these disparities. If galaxies were discrete entities, had they always existed in their present configurations? Did they evolve over billions of years, or were they static formations? The light emanating from distant galaxies required millions, or even billions of years to reach Earth, but telescopes lacked the power to penetrate far enough into the past to study the earliest galaxies. Scientists could only observe the galaxies accessible to them and formulate educated hypotheses about their history. Despite these pervasive uncertainties, the assertion that Andromeda was a galaxy gained widespread acceptance. The supporting evidence was overwhelmingly compelling. Yet, each resolution unearthed new enigmas, underscoring that the study of galaxies was only nascent. Deciphering Andromeda's intricate composition. Andromeda, also known as Messier 31 or M31, eventually ascended to become one of the most extensively studied galaxies in the observable universe. As astronomers moved beyond the fundamental question of its galactic nature, their attention shifted to comprehending its structure, elemental makeup, and concealed complexities. What they discovered was a vast cosmic structure replete with billions of stars, swirling gaseous nebulae, enigmatic halos of dark matter, and a history of galactic mergers that had sculpted it over eons. Analogous to the Milky Way, Andromeda hosts stars of diverse ages, ranging from youthful blue giants to venerable red dwarfs that have continuously radiated for billions of years. Within its brilliantly illuminated central region, older, redder stars predominate, suggesting a protracted history of stellar evolution. These stars coalesced early in the galaxy's existence, consuming a significant portion of the available gas. However, within its spiraling arms, where dense clouds of gas and dust still persist, younger stars are perpetually being born. These areas shimmer with the radiance of intensely hot blue stars that have formed relatively recently from an astronomical perspective. A galaxy composed solely of ancient stars would imply a cessation of new star formation long ago, whereas a galaxy densely populated with young stars would suggest it was still in its formative stages. Andromeda, however, presents a hybrid of both, indicating it has undergone recurrent cycles of star formation. At times, it has experienced bursts of prolific star creation, while at other times, it has remained relatively dormant. These cycles are propelled by the movement and interplay of gas, which serves as the fundamental raw material for stellar genesis. Andromeda's extensive reservoirs of gas and dust offer crucial insights into the galaxy's ongoing evolutionary trajectory. Hydrogen, the universe's most abundant element, constitutes a significant portion of the gas within the galaxy. Vast clouds of hydrogen drift between the stars, occasionally coalescing into dense regions where gravity compels the material to aggregate. If a sufficient quantity of gas accumulates in a single location, the pressure and temperature escalate until nuclear fusion is ignited, leading to the birth of a new star. In certain locales, entire stellar clusters emerge from a single massive gaseous cloud. Some of the gas exhibits movement inconsistent with the rest of the galaxy, suggesting that Andromeda has incorporated smaller galaxies over extended periods. When a diminutive galaxy ventures too close, Andromeda's gravitational pull draws it in, stripping away its stars and gas, and assimilating them into its own structure. These galactic fusions have left behind faint stellar streams and disrupted gaseous patterns, serving as residual evidence of past cosmic collisions. Encircling the galaxy is an immense halo of invisible material that neither emits nor reflects light. This elusive substance, designated as dark matter, is believed to constitute the majority of Andromeda's mass. Nevertheless, it remains undetectable, its presence inferred solely through its gravitational influence. Astronomers first conjectured the existence of dark matter while analyzing galactic rotation patterns. In a typical celestial system, stars and gas at the periphery of a galaxy ought to orbit at slower velocities than those nearer the center, analogous to the slower orbital speeds of planets farther from the Sun in our solar system. However, observations revealed that Andromeda's outermost stars move with speeds comparable to those closer to its core. The sole plausible explanation was the presence of an unseen mass exerting additional gravitational force, effectively anchoring the stars in their orbits. Through the meticulous study of stellar and gaseous kinematics, scientists have estimated that Andromeda possesses a significantly greater proportion of dark matter than ordinary matter. The visible stars, gas, and dust account for only a fraction of the galaxy's total mass. The remainder is sequestered within this imperceptible component, forming a colossal halo that extends far beyond the galaxy's primary disk. This dark matter is theorized to function as a cosmic scaffolding, influencing the genesis and evolution of galaxies. Yet, despite decades of dedicated research, its precise nature remains an unresolved mystery. Andromeda's architectural framework also encompasses a luminous central bulge, a substantial disk of stars, and expansive spiral arms. The galaxy's core is densely populated with ancient stars, encircling a supermassive black hole at its nexus. This black hole possesses a mass millions of times that of our Sun, although it appears to be less active than those observed in other galaxies. It does not accrete substantial quantities of matter. Consequently, it does not generate the powerful jets and radiation characteristic of more energetic galaxies. Progressing outward from the core, the thick stellar disk extends across a vast expanse, with spiral arms curving outward in a recognizable pattern. These arms are not solid structures, but rather represent propagating waves of density that traverse the galaxy, stimulating star formation as they sweep through gaseous nebulae. Over time, these arms undergo shifts and transformations, influenced by the gravitational influence of Andromeda's numerous smaller satellite galaxies. Andromeda is orbited by dozens of lesser galaxies, much like moons encircling a planet. These include dwarf galaxies such as M32 and M110, which are progressively being disrupted by Andromeda's gravitational embrace. Some of these diminutive galaxies may eventually be fully absorbed, their constituent stars and gas contributing to Andromeda's burgeoning structure. The galaxy also harbors a vast population of globular clusters, dense congregations of tightly packed stars that orbit the central region. These clusters contain some of Andromeda's most ancient stars, relics from its earliest epochs. The study of these clusters offers profound insights into the processes of galactic formation and evolution over cosmic timescales, as they serve as ancient archives of conditions that prevailed billions of years ago. Recent investigations of Andromeda have uncovered even more unexpected features. Astronomers have identified a vast, planar arrangement of dwarf galaxies orbiting the principal galaxy in a synchronized fashion, a configuration that challenges prevailing theories of galactic formation. The rationale behind this alignment remains obscure, as simulations suggest that satellite galaxies should exhibit random distributions rather than adherence to a flat plane. Another surprising revelation is the discovery that Andromeda has experienced at least one major merger event in its past. While the Milky Way has primarily grown through the assimilation of smaller galaxies, Andromeda appears to have collided with a larger system at some point in its history. This ancient merger significantly reconfigured the galaxy's structure, scattering stars and gas across immense distances. The evidence for this event is derived from the motion of stars within Andromeda's outer halo, where vestiges of a prior galaxy still persist. As the closest major galaxy to the Milky Way, Andromeda serves as an invaluable cosmic laboratory for understanding galactic dynamics. Scientists are actively engaged in determining how its supermassive black hole influences the surrounding stellar populations, and how its satellite galaxies interact with its larger structure. The advent of new telescopes and instruments promises to yield even more profound insights, enabling astronomers to map the galaxy with unprecedented detail. The cosmic palette, Andromeda's distinctive chemical signatures. Just as a forensic investigator meticulously examines residual traces at a crime scene, astronomers analyze the light emitted by Andromeda to ascertain the elemental composition of its stars, gas, and dust. This chemical fingerprint is unique, sculpted by billions of years of stellar evolution, cosmic collisions, and the perpetual recycling of matter. The most prevalent element within Andromeda, consistent with the broader universe, is hydrogen. It stands as the simplest and most abundant element, serving as the primary fuel for stellar genesis. Alongside hydrogen, helium is also present in substantial quantities, a product of the universe's initial moments during the Big Bang. These two elements provided the foundational constituents for stars. However, what imbues Andromeda with its unique chemical character are the heavier elements that have been synthesized within its stars over eons. As stars progress through their life cycles, they forge new elements via nuclear fusion. Lighter elements, such as carbon, nitrogen, and oxygen, are synthesized in smaller stars, whereas heavier elements like iron, nickel, and gold emerge from more massive stars and cataclysmic supernova explosions. These newly created elements are dispersed into space upon stellar demise, mingling with the surrounding gas and dust. This cyclical process continues as subsequent generations of stars form from this enriched material, each possessing a subtly distinct chemical makeup from its predecessor. The chemical heterogeneity within Andromeda is not uniform. The galaxy's oldest stars, located in its halo and formed billions of years ago, contain fewer heavy elements compared to the younger stars found within the spiral arms. This disparity arises because these primordial stars coalesce before the accumulation of many heavier elements. Conversely, the spiral arms, where ongoing star formation transpires, are exceptionally rich in metals. Astronomers classify all elements heavier than helium as metals, denoting their enrichment through multiple stellar generations. One of the most remarkable chemical characteristics of Andromeda is the presence of unusual isotopic ratios. Isotopes represent distinct manifestations of an element, sharing the identical proton count but differing in their neutron numbers. Specific isotopic forms, such as those of oxygen and carbon, offer profound insights into the cosmic phenomena that have sculpted our galaxy. Researchers have identified disparities in these isotopic proportions when juxtaposing Andromeda with the Milky Way, implying divergent developmental trajectories for the two galaxies. These variances can be attributed to the stellar types that contributed to Andromeda's elemental composition. Certain isotopes are synthesized within the extreme temperatures of colossal stars, while others originate from less energetic, smaller stars. By scrutinizing the prevalence of these isotopes, astrophysicists can ascertain which stellar categories were paramount in shaping Andromeda's makeup. The observed patterns suggest that Andromeda has experienced a distinct rate of stellar genesis and potentially different types of stellar cataclysms when contrasted with the Milky Way. When a galaxy undergoes a merger, it not only assimilates stellar bodies, but also acquires any unique chemical signatures inherent to the encroaching celestial entity. The peripheral zones of Andromeda exhibit traces of elements that deviate from the standard composition of its primary disk. These could be vestiges of long-vanished galaxies that were absorbed by Andromeda, leaving behind imprints of their singular chemical identities. The galactic nucleus displays a greater density of iron and other weighty elements compared to its surrounding environs. This indicates that Andromeda's core may have undergone periods of intense star formation and supernova activity in its past. Some of these elements might have been forged in short-lived, massive stars that detonated violently, seeding the adjacent space with heavier elements. This process mirrors observations in other galaxies exhibiting active star-forming regions. Certain investigations have proposed that Andromeda possesses a somewhat diminished proportion of specific elements, such as magnesium, compared to what would be anticipated for a galaxy of its magnitude and age. This could signify that Andromeda's chemical evolution was influenced by external factors, such as variations in its primordial environment or past interactions with other galaxies that altered its star formation chronology. Granules of dust, comprising microscopic solid particles of carbon, silicon, and other elements, are dispersed throughout the galaxy. These dust particles play a crucial role in the creation of new stars and planets, serving as the fundamental building blocks for planetary systems. The chemical makeup of this dust varies across the galaxy. Some regions are richer in carbonaceous grains, while others are dominated by silicate particles, akin to the rocky materials found on Earth. One of the principal instruments scientists employ to dissect Andromeda's chemical composition is spectroscopy. By examining the light emitted or absorbed by diverse elements, astronomers can precisely determine the galaxy's elemental makeup. This methodology has unveiled the presence of molecules like carbon monoxide, frequently found in dense nebulae where new stars are being born. The identification of these molecules assists researchers in comprehending Andromeda's ongoing evolution and its capacity to generate subsequent generations of stars. As the galaxy continues its process of star creation, its overall metallicity, defined as the abundance of elements heavier than helium, will augment. However, as its reservoir of primordial gas gradually depletes, the pace of star formation will decelerate. Ultimately, Andromeda will transform into a galaxy characterized by older stars, with diminished rates of new stellar birth. Upon its eventual amalgamation with the Milky Way, anticipated in approximately 4 billion years, the resultant composite galaxy will bear the chemical imprints of both constituent systems, blending their histories into a novel cosmic identity. Andromeda harbors an immense diversity of celestial bodies, many of which adhere to predictable life cycles and align with astronomical observations in other galaxies. Nevertheless, interspersed among these commonplace stars are certain rare and peculiar types. Some are the aftermath of cataclysmic cosmic occurrences, while others are still in the process of formation in manners that challenge contemporary astrophysical models of stellar genesis. Among the most captivating categories of rare stars in Andromeda are luminous blue variables. These stars are substantial, unstable, and prone to abrupt fluctuations in luminosity. They exist in a precarious equilibrium between gravitational pull and radiative pressure, with their outermost envelopes frequently being expelled by powerful stellar winds. A prominent example of a luminous blue variable in Andromeda is A Andromeda, whose brightness has been observed to vary over time. These stars are believed to occupy a transient phase of their evolution prior to their explosive demise as supernovae, rendering them pivotal subjects for understanding the terminal stages of massive stars. Dispersed throughout Andromeda's spiral arms are numerous Wolf-Rayet stars, an uncommon and extreme class of hot, massive stars approaching the end of their lifespans. These stars have already shed the majority of their outer hydrogen envelopes, exposing the deeper, hotter regions where heavier elements are being synthesized. Consequently, Wolf-Rayet stars generate potent stellar winds and radiate an intense blue-white luminescence. Their presence signifies areas of recent stellar formation, as they persist for only a few million years before succumbing to cataclysmic supernova collapses. Then, there are Andromeda's hypervelocity stars, celestial bodies traveling at extraordinary speeds that would be improbable under normal circumstances. Some of these stars might have been expelled from binary systems following the supernova explosion of their companions. Others could have been propelled outward subsequent to a close encounter with Andromeda's supermassive black hole. These hypervelocity stars traverse at such velocities that some may eventually depart the galaxy entirely, carrying with them evidence of the extreme gravitational forces at play within Andromeda. In the distant peripheries of the galaxy, a different kind of rare star resides: carbon stars. These stars possess an unusual abundance of carbon in their atmospheres, imbuing them with a distinctive reddish hue. Carbon stars are thought to form when convection currents within the star bring carbon from deeper strata to the surface, enriching the outer atmosphere. This process alters the star's light emission, making it appear redder than usual. Andromeda's carbon stars are particularly noteworthy, as they offer insights into the cyclical nature of chemical element recycling within galaxies over eons. These stars release carbon-rich material into space, contributing to the enrichment of the interstellar medium with the raw constituents necessary for subsequent stellar and planetary formation. Deep within Andromeda's central bulge, astronomers have discovered a peculiar population of exceptionally metal-poor stars. These stars originated during the galaxy's early history, when heavier elements were considerably scarcer. These stellar relics date back to a period when the universe was significantly younger, and their elemental compositions provide a glimpse into the conditions prevailing billions of years ago. Due to their paucity of heavy elements, they are considered among Andromeda's oldest stars, potentially dating to the galaxy's nascent stages of formation. Yellow supergiants represent stars in a brief transitional phase, bridging the gap between red supergiants and blue supergiants, rendering them challenging to observe. Yellow supergiants are infrequent because their evolutionary stage lasts merely a few thousand years, a fleeting moment in cosmic timescales. Their presence in Andromeda furnishes vital data concerning the life cycles of massive stars, aiding astronomers in refining their models of stellar evolution. Perhaps one of the most peculiar categories of stars in Andromeda are magnet stars, neutron stars characterized by extraordinarily potent magnetic fields. These remnants of collapsed massive stars emit bursts of high-energy radiation and possess magnetic fields trillions of times stronger than Earth's. The detection of magnet Rs in Andromeda suggests that the galaxy has undergone a substantial number of supernova explosions, each potentially leaving behind one of these highly magnetized remnants. The study of these objects enables scientists to investigate extreme physics in ways unattainable in terrestrial laboratories. Variable white dwarfs, tiny yet dense remnants of deceased stars, occasionally exhibit unexpected fluctuations in brightness, which can be attributed to pulsations or interactions with surrounding matter. Unlike more common white dwarfs, these infrequent variants may be components of binary systems, wherein they gradually accrete material from a companion star. In certain instances, this process can precipitate a sudden thermonuclear explosion known as a nova, momentarily amplifying the white dwarf's luminosity by thousands of times before it recedes into obscurity. Each novel observation contributes to the expanding comprehension of stellar evolution, the temporal transformations of galaxies, and the influence of diverse cosmic environments on stellar life cycles. These often overlooked luminaries, frequently relegated to peripheral roles in broader galactic discussions, offer essential clues about Andromeda's past and future, demonstrating that even within a thoroughly studied galaxy, mysteries persist, awaiting discovery. Andromeda is not merely an aggregation of isolated stars, but a vast cosmic expanse where stars congregate in clusters, forming self-evolving communities. Some of these clusters are dense and ancient, while others are loosely bound and comparatively young. Among the most conspicuous cluster types found in Andromeda is the population of globular clusters. These compact, spherical congregations of stars represent some of the oldest structures within any galaxy, often containing stars that originated early in cosmic history. Andromeda possesses a significantly greater number of globular clusters than the Milky Way, with estimates exceeding 500 orbiting the galaxy. However, some of these clusters exhibit characteristics distinct from those typically observed in other galaxies. A few contain stars considerably younger than anticipated, prompting questions about their formation mechanisms. Others display anomalous motions, suggesting they might not have been indigenous to Andromeda, but were captured from smaller galaxies during past collisions. Astronomers have also identified a surprising quantity of extended clusters in Andromeda, groups of stars that, while less densely packed than traditional globular clusters, remain gravitationally bound. These clusters are unusual as they blur the distinction between star clusters and minor galaxies. In contrast to typical, tightly bound, and relatively spherical globular clusters, extended clusters possess more dispersed structures and lower overall densities. Some scientists posit that these entities might represent an intermediate stage between clusters and dwarf galaxies, providing a rare window into the evolutionary processes of galactic structures over time. A particularly enigmatic type of star cluster in Andromeda is the so-called faint fuzzy cluster. These clusters were initially identified in Andromeda's outer regions and appear distinct from both globular and open clusters. They contain ancient stars akin to those in globular clusters, but exhibit looser configurations, making them less likely to persist for billions of years without disruption from gravitational forces. Some theories propose they might be remnants of a long-past merger between Andromeda and a smaller galaxy, slowly dispersing over time. Andromeda also hosts an unexpected abundance of young, massive clusters, comprising brilliant, hot stars only a few million years old. The presence of these young clusters is surprising, given that many are situated in regions where star formation was presumed to have largely ceased. Several of these clusters are located far from Andromeda's primary star-forming zones, fueling speculation that they may have originated from tidal interactions or been triggered by prior collisions with satellite galaxies. There exist star clusters whose chemical composition diverges from that of the broader galaxy. Some of these contain stars with anomalous elemental ratios. A few clusters even display compositions more akin to those found in dwarf galaxies rather than in a grand spiral galaxy like Andromeda. This suggests that Andromeda has been incorporating smaller galaxies over time, with their star clusters becoming integrated into its stellar population. The study of these clusters provides evidence of Andromeda's history of mergers and acquisitions, enabling astronomers to reconstruct past events that shaped the galaxy into its current form. The spatial distribution of star clusters also raises questions. Some clusters are found in locations where they should have long since been dispersed by gravitational forces, while others form patterns suggesting an origin from larger structures. Certain clusters even appear to be arranged in streams or arcs, possibly remnants of past mergers. These configurations indicate that Andromeda's halo is still undergoing formation through ongoing interactions with smaller galaxies. A subset of Andromeda's often overlooked clusters are even more challenging to categorize. A handful of clusters appear to contain exceptionally massive stars that should not have survived for billions of years. Others harbor an unusual mixture of stars, with some appearing significantly younger than expected. These anomalies have spurred speculation that some clusters might be ephemeral, held together only loosely by gravity, and destined to eventually dissolve into Andromeda's general stellar population. Advanced telescopic observations have revealed additional star clusters concealed within the dense regions near Andromeda's core, previously obscured by dust and intense stellar light. These central clusters may hold clues concerning the supermassive black hole at Andromeda's center, potentially interacting with its formidable gravitational forces. Other discoveries include star clusters situated at extreme distances from the galaxy, posing questions about the extent of Andromeda's influence into intergalactic space. At the nexus of Andromeda resides one of its most formidable constituents, a supermassive black hole. This immense object, concealed deep within the galaxy's core, exerts influence over its entire surroundings, dictating stellar trajectories, distorting light, and engulfing matter that ventures too close. For a considerable period, scientists have hypothesized that the majority of large galaxies harbor such central black holes. Observational data indicate that Andromeda's supermassive black hole, designated M31*, possesses a mass approximately 140 million times that of the Sun, making it considerably more massive than the Milky Way's central black hole, Sagittarius A star. The existence of such a colossal object at Andromeda's core prompts inquiries into its formation and growth. Some theories propose that as Andromeda assimilated smaller galaxies over billions of years, each contributed its own black hole, which subsequently merged to form a singular, larger entity at the galaxy's center. Encircling M31* is a dense, compact stellar aggregation, an anomalous feature distinguishing it from other galactic cores. These stars traverse at incredible velocities, drawn by the black hole's immense gravitational pull. Observing these motions aided astronomers in confirming the black hole's existence, as only such an extreme concentration of mass could account for the star's behavior. In contrast to some other galaxies, M31* does not currently appear to be accreting substantial amounts of matter. Many galactic central black holes form what is termed an active galactic nucleus, characterized by swirling gas and dust that heats up, producing intense radiation. Andromeda's black hole, however, remains relatively quiescent, emitting only minimal X-ray and radio wave radiation. Scientists theorize this might be a temporary state. It is plausible that in the past, the black hole was more active, consuming matter and releasing energy that could have shaped Andromeda's core. Future encounters with gas clouds, or even entire star systems could reanimate it, transforming it into a more dynamic and energetic feature of the galaxy. Beyond the central black hole, Andromeda might also harbor smaller intermediate mass black holes, dispersed throughout its structure. These black holes, ranging from hundreds to thousands of times the Sun's mass, are believed to originate from the collapse of massive stars or the merging of smaller black holes. While supermassive black holes dominate galactic centers, intermediate mass black holes remain elusive and are among the most difficult astronomical objects to detect. Some of these smaller black holes may reside within the dense star clusters orbiting Andromeda. There is mounting evidence suggesting that certain globular clusters may contain central black holes, influencing the motion of surrounding stars. If confirmed, these intermediate mass black holes could elucidate the mechanisms by which supermassive black holes grow over time. Scientists have even postulated that some of Andromeda's clusters might contain multiple black holes, engendering complex gravitational interactions that could ultimately lead to the formation of a larger black hole through repeated mergers. Wandering black holes do not maintain fixed positions, but drift through the galaxy. These black holes may have originated from past galactic collisions, being ejected from their initial locations by powerful gravitational forces. Some could be the remnants of smaller galaxies that Andromeda has consumed. Black holes are exceedingly challenging to detect unless they interact with nearby matter. However, their gravitational influence can occasionally be observed when they pass in front of a distant star, momentarily bending and magnifying its light through a phenomenon known as gravitational lensing. These entities, though invisible to the naked eye, exert potent gravitational forces capable of influencing star formation, disrupting planetary systems, and even altering the trajectories of entire star clusters. If Andromeda contains a significant population of these hidden black holes, they could play a crucial role in its evolution. Gravitational wave detectors, sensitive to spacetime ripples generated by merging black holes, may also aid in identifying concealed black holes within Andromeda. As technology advances, astronomers will gain the capacity to investigate these enigmatic objects with greater precision, uncovering more about their origins and their impact on the galaxy. Without dark matter, Andromeda, along with the Milky Way and countless other galaxies, would not exist in its present configuration. One of the initial indicators of dark matter's presence in Andromeda emerged from the analysis of the galaxy's rotational patterns. If Andromeda comprised solely of the observable stars, gas, and dust detected by astronomers, then the outer regions of the galaxy should exhibit significantly slower rotational velocities compared to the inner portions. The most straightforward explanation is that Andromeda is enveloped by an extensive halo of unseen material, extending far beyond its visible periphery and possessing a mass greater than all its stars and gas combined. The sheer magnitude of mass required to account for Andromeda's motion suggests that dark matter constitutes the majority of the galaxy's total mass. If the stars, planets, and gas clouds comprising Andromeda were the sole constituents, their collective gravitational force would be insufficient to maintain the galaxy's structural integrity. The distribution of dark matter within Andromeda is not uniform. Certain regions exhibit higher concentrations than others. Scientists have mapped dark matter through gravitational lensing, studying the deflection of light as it traverses different parts of Andromeda's halo to reconstruct an image of this invisible substance. These investigations indicate that dark matter isn't uniformly distributed but rather possesses a clumpy configuration, potentially influenced by engagements with lesser companion galaxies or the gravitational forces inherent within Andromeda itself. The existence of dark matter also impacts how Andromeda interacts with its neighboring galaxies. Andromeda is a member of the Local Group, a cosmic assemblage encompassing the Milky Way and numerous smaller galaxies. The gravitational influence of dark matter within Andromeda's halo extends well beyond its visible periphery, affecting the trajectories of nearby galaxies. Some of these galaxies, such as the dwarf companions that orbit Andromeda, might be anchored by the gravity of dark matter, preventing their escape into the vastness of space. Conversely, others could be slowly descending towards Andromeda, drawn by its unseen mass. A significant enigma surrounding dark matter in Andromeda concerns its behavior during the galaxy's predicted collision with the Milky Way, an event anticipated in several billion years. The visible stars and gas clouds of both galaxies will engage in dramatic interactions, leading to the formation of new stellar clusters and modifications of their structures. Dark matter, however, not interacting in the same manner, will behave differently. Instead of direct collisions, the dark matter halos of the two galaxies will interpenetrate, their immense gravitational forces reshaping the resulting merged galaxy. If dark matter is composed of weakly interacting particles, as numerous theories posit, its distribution following the collision could furnish insights into its properties. Alternatively, if dark matter exhibits some degree of self-interaction, unexpected patterns might emerge in the galaxy merger process. Did dark matter originate concurrently with the rest of the galaxy, or was it already present in the early universe, shaping the nascent galaxies long before stellar ignition? Certain hypotheses suggest that dark matter particles were generated in the immediate aftermath of the Big Bang, dispersing throughout the cosmos, and serving as the foundation upon which galaxies, like Andromeda, subsequently formed. Others propose that dark matter might be linked to currently unknown forces or particles yet to be discovered. Scientists aspire that by meticulously charting dark matter's distribution and observing its effects on Andromeda's stellar population, they may eventually unravel the mystery of this invisible yet crucial component of the universe. Mapping the grand innovations in galactic cartography presents one of the most formidable challenges due to Andromeda's sheer immensity. Despite being the closest major galaxy to the Milky Way, its entire structure does not fit conveniently within the field of view of most telescopes. Capturing a complete view necessitates assembling numerous smaller images, a process demanding years of dedicated effort. The Hubble Space Telescope produced one of the most detailed portrayals of Andromeda by integrating thousands of individual exposures, creating a mosaic that revealed millions of stars across an extensive expanse of the galaxy. Charting Andromeda involves more than mere image acquisition. Researchers must also precisely measure distances, analyze stellar and gaseous motion, and ascertain the elemental composition of various regions. A pivotal technique employed in galactic mapping is spectroscopy, which aids in determining the chemical makeup, temperature, and motion of stars and gaseous clouds. This enables scientists not only to pinpoint the locations of celestial bodies, but also to understand their interrelationships and the galaxy's temporal evolution. Motion mapping constitutes another indispensable tool. Andromeda is not a static entity. It rotates, shifts, and even assimilates smaller galaxies. To chronicle these movements, astronomers utilize Doppler shifts, which quantify the alteration in light wavelengths as an object approaches or recedes from us. By scrutinizing these shifts across diverse segments of Andromeda, scientists can generate a comprehensive rotational map, illustrating how different areas spin at varying velocities. Interstellar dust scatters and absorbs light, impeding observation of certain galactic regions, some of which remain almost entirely obscured in visible light. To circumvent this limitation, astronomers employ infrared telescopes capable of penetrating dust clouds and revealing structures that would otherwise be hidden. The Spitzer Space Telescope offered a novel perspective on Andromeda by mapping its dust-rich areas, providing insights into nascent star formation zones. Andromeda harbors substantial quantities of hydrogen gas, which emits radio waves at a specific wavelength detectable even in regions where visible light is obstructed. By charting these emissions, scientists can construct a detailed map of Andromeda's gas distribution, indicating likely sites of new star birth and the mechanisms by which the galaxy replenishes its stellar population. Advances in computational modeling have also revolutionized galactic mapping. Rather than relying solely on direct observations, astronomers now employ simulations to reconstruct Andromeda's structure. These models integrate all relevant factors, from stellar distribution to dark matter influences and gravitational interactions with other galaxies. By juxtaposing simulated representations of Andromeda with actual observations, scientists can refine their comprehension of the galaxy's formation and evolutionary trajectory. Its companion galaxies are also meticulously catalogued. While some, such as M32 and M110, are readily apparent, others remain elusive. Extensive surveys have unveiled a comprehensive system of dwarf galaxies. Monitoring these satellites assists astronomers in comprehending Andromeda's gravitational dominance and offers insights into the growth mechanisms of large galaxies through the assimilation of smaller ones. One of the most ambitious mapping initiatives is dedicated to charting Andromeda's impending rendezvous with the Milky Way. Scientists are leveraging detailed observations and motion analysis to predict with precision the intricate interactions that will occur when the two galaxies commence their merger in approximately 4.5 billion years. By charting the movement of stars and gas within Andromeda, astronomers have successfully developed computer models that simulate the eventual amalgamation of the galaxies, giving rise to a new, larger structure in the distant future. Numerous enigmas persist. Certain regions of the galaxy remain poorly understood, necessitating novel technologies to unveil their secrets. Future space observatories, such as the forthcoming Nancy Grace Roman Space Telescope, are anticipated to deliver even more granular maps of Andromeda, empowering astronomers to study individual stars, identify concealed structures, and enhance existing models. Andromeda's celestial companions, its satellite galaxies, are numerous. Surrounding Andromeda are dozens of smaller galaxies, each intricately orbiting and interacting with the colossal spiral in complex dynamics. They exhibit a diversity of sizes and shapes, ranging from compact elliptical dwarfs to irregular systems seemingly undergoing disintegration. Some are easily discernible, even with amateur telescopes. M32 and M110 are the most prominent, situated relatively near Andromeda's luminous central region. M32 is a compact elliptical galaxy with a dense stellar concentration, whereas M110 is slightly larger and more dispersed, showing indications of past interactions with its massive host. Both are considered remnants of larger galaxies from which Andromeda has long ago stripped gas and outer layers. Beyond these conspicuous companions, numerous fainter dwarf galaxies orbit Andromeda at greater distances. Some, like NGC 147 and NGC 185, possess structures reminiscent of diminutive elliptical galaxies, characterized by minimal star formation activity and an aging stellar population. Others, such as IC-10, are still actively forming stars, suggesting they have retained their gas reserves despite Andromeda's gravitational pull. Initial models indicated that these satellite galaxies should be randomly distributed, orbiting in various directions without a discernible pattern. However, recent observations have revealed an unexpected arrangement. Many of Andromeda's satellites appear to be situated within a vast, thin plane rather than being uniformly dispersed in space. This discovery challenges prevailing theories of galaxy formation, implying that these satellites might have originated from a singular event rather than being independent objects acquired over time. Some astronomers posit that Andromeda's satellite system is part of a much grander configuration, potentially linked to the Milky Way's own collection of dwarf galaxies. The concept is that these diminutive galaxies might not be isolated entities, but rather components of immense cosmic filaments, elongated structures of dark matter, and gas stretching between galaxy clusters. Some of these satellites are undergoing consumption, their stars and gas stretched into long streams as they spiral inward. Observations have detected immense arcs of stars and gas extending away from Andromeda, believed to be the remnants of prior mergers. These streams provide direct evidence that Andromeda has augmented its mass by absorbing smaller galaxies, a process that continues to this day. One of the most evident instances of this galactic cannibalism is the discovery of the giant stellar stream, an expansive ribbon of stars stretching over 100,000 light-years across space. This stream is thought to represent the remnants of a dwarf galaxy that ventured too close to Andromeda and was progressively disintegrated by tidal forces. Its stars, once part of a smaller, independent system, are now integrating into Andromeda's halo, blending into the larger galaxy's population. These interactions are not unilateral. While Andromeda exerts the dominant influence, its satellite galaxies can also subtly affect their host. Their collective gravitational pull can influence the contours of Andromeda's outer regions, inducing minor distortions in its disk. Over extended periods, these interactions may even impact Andromeda's overall structure, contributing to its future evolution. Given that these dwarf galaxies are small and faint, their motion is significantly influenced by the surrounding dark matter. By tracking their orbital paths, astronomers can infer the distribution of dark matter around Andromeda. Some of Andromeda's satellites appear to consist almost entirely of dark matter. These so-called dark galaxies contain very few stars and minimal visible gas, yet possess sufficient mass to be detected through their gravitational effects. Their existence raises intriguing questions regarding galaxy formation and the potential prevalence of these nearly invisible objects throughout the universe. Some will eventually merge with Andromeda, their stars becoming assimilated into the larger galaxy. Others may be expelled into deep space due to gravitational interactions. As Andromeda itself draws nearer to the Milky Way, its satellite system will also be affected, potentially leading to new collisions and mergers in the distant future. Supernova remnants, the lingering echoes of explosive transformations, mark the end of a massive star's life. This occurs either through the abrupt collapse of a single colossal star or the violent disintegration of a white dwarf within a binary system. The ensuing explosion unleashes an immense quantity of energy, propelling heavy elements into space and generating shock waves that propagate through the surrounding regions. Within Andromeda, these cataclysmic events have been instrumental in enriching the galaxy with new elements, sculpting nebulae, and even influencing the genesis of new stars. One of the most thoroughly documented supernova remnants in Andromeda is the remnant of SN 1885A, a supernova observed from Earth in the year 1885. Unlike many others that fade into obscurity, this remnant remains a significant subject of scientific inquiry. It was a Type I supernova, resulting from a white dwarf in a binary system accumulating excessive mass and undergoing a runaway thermonuclear explosion. What renders SN 1885 a particularly captivating is its proximity to Andromeda's core. The explosion left behind traces of iron and other heavy elements. Even today, astronomers can detect its faint signature when observing the region. This supernova helped confirm that Andromeda shares similarities with the Milky Way in its capacity to host such colossal cosmic occurrences. Beyond individual instances, Andromeda harbors an extensive network of supernova remnants, many of which are only discernible through X-ray and radio observations. These remnants manifest as luminous shells of expanding gas, still energized by the shock waves from the original explosion. Some are relatively young, only a few thousand years old, actively shaping the space around them. Others are more ancient, their initial structures having merged into the interstellar medium as their energy gradually dissipates. The shock waves they generate agitate surrounding gas clouds, compressing them and occasionally initiating the formation of new stars. Without these explosions recycling elements and distributing them throughout the galaxy, Andromeda and all other galaxies would present a vastly different appearance. The heavier elements essential for rocky planets, life, and even the fundamental chemistry of the universe owe their existence to these powerful cosmic detonations. By mapping these remnants, astronomers can trace the distribution of older stellar populations, identifying regions where past generations of massive stars once flourished. Numerous remnants are found within the spiral arms, areas of intense star formation activity spanning millions of years. However, others are detected in less expected locations, hinting at past bursts of activity that might not have been evident through other observational methods. Some remnants in Andromeda are notable for their unusually high energy output. These remnants, often associated with rapidly rotating neutron stars or pulsars, suggest that certain supernovae left behind more than mere expanding gas clouds. Instead, they engendered dense, swiftly rotating stellar remnants that continue to emit radiation long after the initial explosion. These pulsars serve as cosmic beacons, aiding astronomers in probing the physics of extreme matter and the forces at play in Andromeda's evolutionary process. The impact of these stellar explosions extends beyond the boundaries of the remnants themselves. The expanding shock waves interact with interstellar clouds, altering their chemical composition. They accelerate cosmic rays, high-energy particles that travel through space at velocities approaching the speed of light. These cosmic rays contribute to the heating and ionization of gas within Andromeda, influencing the conditions under which new stars form. The appearance of certain supernova remnants in unexpected locations, or with anomalous properties, could indicate that Andromeda has assimilated material from past mergers. Some of the most ancient remnants might not have originated within Andromeda itself, but rather from dwarf galaxies that were consumed by its gravitational pull. Variable stars, the rhythmic pulses in the galactic heartbeat, are among astronomy's most valuable instruments, serving as natural beacons that assist astronomers in measuring distances, tracking stellar evolution, and comprehending the intricate dynamics of galaxies. These stars do not emit light at a constant intensity. Instead, they fluctuate in brightness over time, sometimes in predictable cycles, and at other times in erratic bursts. Within Andromeda, thousands of variable stars have been identified, each offering a unique perspective on the galaxy's complex dynamics. One of the most renowned categories of variable stars is the Cepheid variable. Even today, Cepheid variables remain exceptionally reliable distance indicators, helping astronomers refine measurements of Andromeda's vast scale. However, they are not the sole pulsating stars dispersed throughout Andromeda. RR Lyrae stars, another class of variable stars, exhibit a similar pattern but are smaller and older. These stars are commonly found in the galaxy's dense halo and globular clusters, regions housing ancient stellar populations. By studying their rhythmic pulsations, astronomers can trace Andromeda's oldest structures, identifying areas that have remained largely unchanged for billions of years. While Cepheids aid in determining distances to galaxies, RR Lyrae stars serve as indicators of ancient stellar movements and past galactic interactions. Variable stars also exist whose luminosity changes due to external factors rather than internal pulsations. Eclipsing binary stars are pairs of stars that orbit each other, periodically obscuring each other's light from our observation. When one star passes in front of the other, the total brightness of the system diminishes. By meticulously analyzing these variations, astronomers can determine the sizes, masses, and orbital parameters of the stars within these systems. Andromeda hosts countless eclipsing binaries, ranging from massive, short-lived blue giants to dim red dwarfs engaged in slow, decade-long orbital dances. Cataclysmic variables, such as novae systems, experience sudden outbursts when material from one star in a binary system accretes onto the other. The abrupt surge of light can cause a previously inconspicuous star to flare dramatically before dimming once more. Long-period variables, like mirror-type stars, exhibit brightness fluctuations over months or even years. These are often red giants nearing the end of their lifespans, pulsating as they shed mass and cool. These aging stars are responsible for seeding Andromeda's interstellar medium with carbon and other elements that will subsequently be incorporated into new generations of stars and planets. By monitoring these long-period variables, astronomers can study the later stages of stellar evolution in real time, observing as old stars transition into planetary nebulae or white dwarfs. Within the central bulge, many variable stars belong to older populations. In the spiral arms, younger variable stars are predominant, including Cepheids and other luminous, short-lived stars born from recent star formation waves. The halo, where globular clusters orbit far from the galactic center, harbors a mixture of RR-Lyrae stars and other ancient variables, tracing the motion of stars that may have once belonged to smaller galaxies absorbed by Andromeda. Unusual spiral structures, patterns, and anomalies present a complex picture. At first glance, Andromeda appears to conform to the classic design of a spiral galaxy, with well-defined arms curving outward from a luminous central bulge. However, certain features deviate from the expected symmetrical form observed in other galaxies, prompting questions about its past and future evolution. One of the initial peculiar aspects of Andromeda's structure is the presence of two superimposed spiral patterns. Unlike the Milky Way, which exhibits a clear, dominant set of arms, Andromeda appears to possess two distinct spirals that do not entirely align. This peculiar double structure is widely believed to be the consequence of a past collision, possibly with one of its satellite galaxies. Another anomaly lies in the uneven luminosity and density of Andromeda's spiral arms. In most spiral galaxies, the arms form distinct, continuous structures where stars, gas, and dust are concentrated. However, in Andromeda, the arms are somewhat fragmented, with varying densities across different regions. Some segments of the arms are densely populated with young, bright stars, while others appear more diffuse and less organized. This uneven distribution suggests that gravitational interactions, both past and present, continue to shape the galaxy's spiral configuration. Beyond the grand spiral arms, Andromeda displays a series of smaller, fainter structures that extend outward in unconventional patterns. These subtle arms and filaments are difficult to perceive with the naked eye but become visible through deep sky imaging. Some of these structures appear to be tidal debris, remnants of past galactic mergers. Others may be the product of density waves, where the movement of stars and gas through the galactic disk creates transient patterns that shift over time. Unlike the primary spiral arms, which remain relatively stable over millions of years, these finer patterns can evolve more rapidly. A particularly striking characteristic of Andromeda's spiral structure is the asymmetry observed in its inner disk. One portion of the galactic core of Andromeda displays a more prominent stellar arm than its counterpart, resulting in an asymmetry. This uneven configuration is atypical for a galaxy of Andromeda's magnitude and suggests an external influence may have contributed to its formation. A conceivable explanation is that Andromeda's planar structure is still stabilizing from a prior encounter with another galaxy. The gravitational pull of a passing or merging galaxy could have drawn stars and gas into a lopsided arrangement, leaving behind a distorted spiral pattern. Some researchers propose that dark matter might account for certain irregularities in Andromeda's spiral structure. As this unseen mass interacts with the visible matter within the galaxy, it could induce disturbances that affect the development and configuration of the spiral arms. In numerous spiral galaxies, the birth of stars is concentrated along the leading edges of the arms, where gas and dust are compressed as they traverse the galactic disk. However, in Andromeda, certain areas of intense star formation are situated beyond the primary spiral arms, creating scattered groupings of young, luminous stars. This observation indicates that the spiral arms alone do not exclusively determine the locations where new stars originate. Other factors, such as the movement of interstellar clouds and shockwaves from past celestial impacts, may also play a crucial role. Unlike the continuous arcs characteristic of a conventional spiral galaxy, Andromeda exhibits several circular formations that resemble faint rings of stars and gas. Some of these rings are believed to be the consequence of earlier collisions, where the impact of a smaller galaxy generated expanding waves that propagated outwards. These rings are likely to dissipate gradually over time, merging into the surrounding spiral arms or transforming into entirely new structures. Extending beyond the visible spiral arms, the galaxy encompasses a vast, faint halo. This expansive disk is not a smooth continuation of the inner spiral architecture, but rather comprises irregular, dynamic patterns. Some of these patterns may be vestiges of ancient gravitational interactions, while others could have been shaped by Andromeda's ongoing gravitational relationship with its smaller companion galaxies. This outer region remains one of the least understood elements of Andromeda's overall structure. In contrast to idealized depictions of perfect spiral galaxies, Andromeda reveals a more dynamic and intricate reality, one where natural forces continuously reshape the galaxy's composition over eons. Beyond our own solar system, the quest for planets in other galaxies is underway. The discovery of worlds outside our solar system has been a monumental advancement in modern astronomy. For many decades, scientists have actively sought exoplanets, which are planets that orbit stars other than our Sun, within the confines of the Milky Way galaxy. Thousands of such planets have been verified, and countless more await detection. However, the ultimate challenge lies in expanding the limits of our observational capabilities even further, specifically to identify planets located in a different galaxy. The Andromeda Galaxy, with its billions of stars, presents an immense frontier for this ambitious search. The detection of exoplanets within the Milky Way is achieved through several established methodologies. The most effective of these is the transit method, which involves observing minute decreases in a star's brightness as a planet passes in front of it. Another significant technique is the radial velocity method, which measures the subtle wobble of a host star caused by the gravitational influence of an orbiting planet. While these techniques are highly successful for planets orbiting stars relatively close to us within our own galaxy, their efficacy diminishes significantly with increasing distance. When observing Andromeda, the immense gulf separating us from its stars renders direct observation nearly impossible with current technological capabilities. Despite these formidable obstacles, astronomers are devising novel approaches to search for planets beyond our galaxy. One particularly promising avenue of research involves the technique known as microlensing. When a massive celestial body, such as a star or even a planet, crosses the line of sight between an observer and a more distant star, it bends and magnifies the light originating from that background star. If a planet is present around the intervening star, its gravitational effect can cause a secondary brightening of the background star's light, thereby revealing its existence. Unlike the transit or radial velocity methods, microlensing does not necessitate direct observation of the planet itself or even the ability to resolve individual stars in a distant galaxy. In the year 2020, astronomers announced the potential discovery of a planet in another galaxy using the microlensing technique. This candidate planet, located in the Whirlpool Galaxy, was identified through subtle disruptions in the X-ray emissions emanating from a binary star system. Although this particular detection remains unconfirmed, it strongly suggests that microlensing could serve as a valuable tool for future discoveries. Applying this method to Andromeda represents a logical progression. The galaxy's densely packed core, filled with numerous overlapping stars, provides an ideal environment for microlensing events to occur. If observed systematically over time, the background stars of Andromeda may exhibit transient brightening patterns that indicate the presence of planetary systems. Andromeda's immense distance presents a significant challenge even in confirming the characteristics of any detected planets. Within the Milky Way, subsequent observations can refine estimations of a planet's size, composition, and atmospheric properties. However, in another galaxy, the most that scientists can currently achieve is indirect evidence of a planet's existence. Ascertaining details such as whether a planet is rocky or gaseous, or if it possesses a substantial atmosphere, remains beyond our current grasp. Future space telescopes equipped with more advanced instruments may eventually provide breakthroughs in this area. Within our own galaxy, astronomers utilize the concept of the habitable zone, which is the region around a star where conditions might permit the existence of liquid water. Many of the exoplanets discovered to date orbit within these zones, raising the possibility that they could harbor life. However, applying this concept to Andromeda is considerably more complex. Even if a planet were found in the appropriate orbit around a suitable star, confirming the presence of water, an atmosphere, or other essential elements for life would be impossible without significantly more sophisticated technology. Given the similarities between Andromeda and the Milky Way, it is highly probable that many types of planetary systems mirror those found closer to home. There would likely be gas giants orbiting their stars at considerable distances, rocky planets in close orbits, or frozen worlds on the galaxy's periphery. Some might bear resemblance to Earth, while others could be entirely alien to anything we have previously encountered. One of the most compelling possibilities is the existence of planets in regions of Andromeda that have experienced substantial stellar interactions. Unlike the Milky Way, which has maintained a relatively stable evolutionary path, Andromeda has undergone mergers with and absorbed numerous smaller galaxies. These mergers can disrupt planetary systems, displacing planets into new orbits or ejecting them into interstellar space. Some scientists hypothesize that Andromeda may host a substantial population of rogue planets, worlds that no longer orbit any star. These wandering planets could be abundant in the galaxy's outer halo, having been dislodged by past gravitational upheavals. If planets do exist within Andromeda, their environments could be profoundly shaped by the unique conditions of their respective locations. In the galaxy's core, planets orbiting stars in the central bulge would be subjected to intense radiation, rendering habitability unlikely. Within the spiral arms, conditions might be more stable, akin to those found in the Milky Way. The presence of supernova remnants, star clusters, and even intermediate-mass black holes in certain regions of Andromeda could create environments where planetary formation is either impeded or significantly altered. The burgeoning field of artificial intelligence is also being integrated into exoplanet research, with machine learning algorithms assisting in the identification of subtle signals within astronomical data. These advancements could ultimately pave the way for the first confirmed detection of planets in Andromeda, ushering in a new epoch in the exploration for worlds beyond our own galaxy and the feasibility of intergalactic travel. Intergalactic travel remains one of the most intricate and speculative challenges in physics. The sheer magnitude of the distances involved renders even the fastest spacecraft ever constructed seemingly impossibly slow. Yet, despite these hurdles, the notion of traversing beyond the Milky Way to reach distant galaxies, like Andromeda, continues to inspire awe. Scientists and engineers have, over the years, explored theoretical frameworks and advanced technologies that could, at some point in the future, make such journeys achievable. The most immediate obstacle is velocity. Andromeda is situated approximately 2.5 million light-years away. This implies that even a spacecraft traveling at the speed of light, a capability currently far beyond our reach, would require 2.5 million years to arrive. The fastest space probe ever created, NASA's Parker Solar Probe, achieves speeds of approximately 430,000 miles per hour. At such a velocity, a voyage to Andromeda would take more than 4,000 times longer than the entire span of human civilization. Clearly, for intergalactic travel to become a reality, an entirely novel form of propulsion is imperative. According to Einstein's theory of relativity, as an object approaches the speed of light, time for its occupant slows down. This means that while an intergalactic expedition might span millions of years, from the perspective of an external observer, the passengers could experience a significantly shorter duration. However, achieving such speeds is vastly beyond our present technological capacity. Conventional rocket propulsion, which relies on chemical reactions, is entirely inadequate. Scientists are investigating more unconventional propulsion methods, including nuclear fusion, antimatter, and even the harnessing of the fabric of space itself. A leading contender is the light sail, propelled by powerful lasers. The Breakthrough Starshot initiative is already exploring this concept, with plans to dispatch minuscule probes to the nearby Alpha Centauri system by accelerating them to 20% of the speed of light using high-intensity laser beams. Scaling this technology for intergalactic voyages would necessitate an immense power source, but theoretically, a sufficiently large array of lasers could propel a spacecraft to speeds approaching that of light. Another strategy is antimatter propulsion. Antimatter is the most energy-dense substance known, releasing colossal amounts of energy upon interaction with ordinary matter. A spacecraft powered by controlled antimatter reactions could attain velocities far exceeding those of chemical rockets. Nevertheless, the production and storage of adequate quantities of antimatter are currently beyond our capabilities. Theoretically, if a spacecraft could achieve speeds close to the speed of light, relativistic time dilation effects would enable travelers to experience the journey to Andromeda in merely a few decades, rather than millions of years. Some scientists have contemplated the utilization of black holes or other extreme astrophysical phenomena to facilitate travel. A concept known as the Alcubierre warp drive, derived from a solution to Einstein's field equations, posits that space itself could be contracted in front of a spacecraft and expanded behind it, thereby enabling effective faster-than-light travel without violating the principles of relativity. This idea is highly theoretical and would demand exotic forms of energy, such as negative mass, which have not yet been empirically observed. There is also the possibility of exploiting naturally occurring cosmic shortcuts. Wormholes, if they exist, could theoretically bridge distant points in space and time, creating a passage that circumvents the vast distances between galaxies. However, no direct evidence of wormholes has been found. And even if they do exist, stabilizing one for safe transit would necessitate unknown varieties of exotic matter. Certain physicists believe that if advanced civilizations exist, they may have already mastered such technologies. Beyond propulsion, the issue of survival becomes paramount. An intergalactic journey spanning thousands, or even millions of years, would require either a means of sustaining life for extended periods, or the ability to place travelers into a state of suspended animation. Hibernation technology, inspired by the dormant states adopted by some animals, is currently undergoing research for long-duration space missions. Cryogenic freezing presents another option, although the biological complexities of safely reviving a frozen human remain unresolved. An alternative to human travel is the deployment of self-replicating robotic probes. This concept, initially put forth by mathematician John von Neumann, suggests that spacecraft equipped with sophisticated artificial intelligence and manufacturing capabilities could journey to distant galaxies, utilize local resources to construct copies of themselves, and continue their voyage indefinitely. Over time, such a system could propagate throughout the universe, collecting and transmitting information without the need for human occupants. While such ideas currently reside firmly within the realm of theoretical speculation, the rapid progression of technology suggests that concepts once deemed impossible may eventually become attainable. Navigating the cosmic void. Challenges of long-distance voyages. Traveling across immense cosmic distances presents a myriad of physical and engineering obstacles that extend far beyond merely achieving high velocities. The vastness of space is not solely a matter of distance, but also encompasses survival, precision, and endurance. For any spacecraft embarking on a mission to depart the Milky Way and navigate the intergalactic void towards Andromeda, it must surmount extreme environmental conditions, energy limitations, potential mechanical failures, and the colossal expanses of emptiness that offer no opportunities for resupply or repair. One of the most immediate concerns involves safeguarding a spacecraft and its occupants from the inherent hazards of deep space. Within our solar system, astronauts are afforded a degree of protection by Earth's magnetic field and the Sun's heliosphere, which deflect a portion of harmful cosmic radiation. However, beyond this protective envelope, the galaxy is permeated with high-energy cosmic rays, particles accelerated to velocities approaching the speed of light by phenomena such as supernovae and black holes. Over prolonged exposure, such radiation would pose severe risks to human travelers, causing DNA damage, elevating cancer risks, and gradually degrading electronic systems. Shielding against this necessitates either exceedingly thick protective layers, which add substantial mass to a spacecraft, or the development of active shielding mechanisms that generate artificial magnetic fields. Even with adequate protection from radiation, intergalactic voyagers would need to contend with the sheer emptiness of space. Unlike within a solar system, where planets, asteroids, and moons occasionally offer opportunities for landing or resource acquisition, the void between galaxies is largely devoid of such features. There are no way stations or natural refueling depots. A spacecraft must carry all necessary provisions for its journey from its inception, including fuel, sustenance, water, and spare components. This introduces a significant engineering challenge: how to store, preserve, and manage such resources for a voyage that could potentially span millions of years. Current chemical rocket technology is entirely insufficient due to its inherent inefficiency. More advanced methods, such as nuclear propulsion or ion drives, offer greater fuel efficiency, but even they may prove inadequate for sustaining a mission lasting thousands of years. One proposed solution involves a spacecraft that continuously gathers fuel as it travels. A theoretical concept known as a Bussard ramjet, for instance, would employ immense electromagnetic fields to scoop hydrogen from interstellar space, utilizing it as fuel for a fusion reactor. While this concept has yet to be empirically validated, it exemplifies the unconventional thinking required for long-distance space travel. Navigation presents another formidable hurdle. Within the solar system, spacecraft rely on radio signals originating from Earth to ascertain their position, and planetary bodies serve as clear reference points. However, in the vast, largely featureless expanse between galaxies, achieving precise positional accuracy becomes considerably more difficult. Stars appear fainter, and conventional navigational markers vanish into the cosmic backdrop. A spacecraft en route to Andromeda would require an autonomous navigation system capable of adjusting its trajectory by utilizing whatever celestial landmarks are available. Pulsar-based navigation, which leverages the consistent signals emitted by rapidly rotating neutron stars, has been suggested as a potential solution. Over a journey spanning thousands of years, wear and tear would be inevitable. Micrometeoroids and interstellar dust, while sparse, could gradually abrade the outer layers of a ship traveling at high velocities. Even minute impacts could, over time, weaken protective shielding and compromise internal systems. Self-repairing materials or robotic maintenance units would likely be indispensable for continuously monitoring and rectifying any damage. If a spacecraft depends on rotating habitats to generate artificial gravity, the mechanical components of these structures must withstand relentless motion without failure. Communication across such immense distances poses yet another formidable challenge. At present, signals transmitted from Earth to even the most distant space probes, such as Voyager 1, require more than 22 hours to reach their destination. A spacecraft journeying toward Andromeda would soon discover that communication delays escalate to weeks, then months, and eventually centuries. If an intergalactic vessel were to transmit a message back to Earth after a millennium of travel, the civilization that initiated its launch might no longer exist by the time the signal arrived. This necessitates a degree of self-sufficiency unprecedented in human exploration. The crew, whether human or artificial intelligence, would need to function entirely independently of Earth's support. Solar power, a reliable energy source within the solar system, becomes considerably less effective in the intergalactic void, where no nearby stars provide sufficient illumination. A spacecraft would require an alternative long-term power source, such as fusion-based energy systems. The challenge lies not merely in generating power, but in doing so sustainably without reliance on constant refueling. If human passengers are on board, maintaining life support systems for extended durations is an even greater concern. A closed-loop ecosystem, where oxygen, water, and nutrients are continuously recycled, would be essential. Even the International Space Station, which depends heavily on supply shipments from Earth, struggles to achieve perfect recycling efficiency. A deep space vessel would need an almost flawless system capable of sustaining life for generations without external input. Hydroponic or aeroponic cultivation could provide sustenance, but ensuring long-term biological stability remains an unresolved issue. The isolation inherent in a multi-generational voyage could have profound psychological and social effects on the crew members. Unlike space missions within our solar system, where astronauts hold the prospect of returning home, intergalactic travelers would be permanently departing Earth. They, or their descendants, would live their entire lives aboard a spacecraft, knowing that they would never reach their intended destination. Social structures, governance, and the preservation of culture over millennia must all be meticulously considered. Some of these challenges could be mitigated if the travelers were not human, but robotic. Advanced artificial intelligence systems designed for independent decision-making and self-repair over extended periods could undertake such missions with fewer concerns regarding life support. However, even machines degrade over time, and software errors or mechanical failures could accumulate. Self-replicating machines capable of repairing and even constructing new iterations of themselves using available materials may offer a viable solution. Simulating the future, Andromeda meets the Milky Way. The future trajectory of our galaxy is not an enigma. Scientists have turned to sophisticated simulations to forecast the events that will unfold when the Milky Way and Andromeda inevitably converge. This colossal cosmic ballet, slated to unfold over the next several billion years, will irrevocably alter the very fabric of both galaxies, with projections revealing its eventual form with remarkable precision. Leveraging prodigious computing power and decades of accumulated observational data, scholars have formulated intricate forecasts detailing the progression of this stately celestial waltz, unveiling a future that is simultaneously tumultuous and captivating. The Andromeda Galaxy is hurtling towards our own Milky Way at an approximate velocity of 110 kilometers per second. At this relentless pace, these galactic behemoths will initiate their inaugural close rendezvous in roughly 4.5 billion years. Unlike the abrupt concussions witnessed in the collisions of asteroids or spacecraft, this celestial encounter is not a sudden impact. The sheer immensity of these galaxies and the vast gulf separating their constituent stars render direct stellar collisions exceedingly improbable. Instead, the colossal gravitational interplay between the two galaxies will contort their morphologies, stretching and elongating them into vast tidal tendrils. These gravitational stresses will sculpt sweeping arcs of stars and interstellar gas, contorting both galaxies into increasingly chaotic configurations before their ultimate assimilation into a singular, more substantial entity. Astronomers meticulously input data pertaining to the mass, velocity, and elemental composition of each galaxy, empowering computers to meticulously calculate the gravitational forces dictating their interactions. By conducting numerous simulations, with infinitesimally varied initial parameters, scientists can delineate a spectrum of potential eventualities. The prevailing scientific consensus, however, posits that Andromeda and the Milky Way will undergo an extended and intricate merger, with each galaxy traversing through the other on multiple occasions before achieving complete amalgamation. The initial pass will undoubtedly be the most spectacular. As the galaxies draw nearer, their mutual gravitational attraction will distort their spiral arms, propelling prodigious streams of stars and gas into the void between galaxies. Andromeda's substantial galactic core is predicted to penetrate the Milky Way, drawing interstellar matter along with it, and igniting prodigious episodes of nascent star genesis. The compression of interstellar gas clouds will precipitate a surge in stellar birth, illuminating the merging galaxies with newly forged suns. Some of these nascent stars will coalesce into prodigious stellar clusters, while others may eventually collapse to form black holes, augmenting the burgeoning population of these enigmatic celestial objects within the nascent galaxy. As the galaxies continue their celestial ballet, they will experience repeated close proximity events. With each successive encounter, gravitational forces will ablate further portions of their original structural integrity. The familiar spiral arms of both galaxies will become progressively disheveled, elongated, and distorted into sweeping tidal tails. Certain stars may be violently ejected entirely, cast into the intergalactic expanse, where they will drift in solitude for eons. Others will settle into novel orbital paths as the two galaxies gradually integrate their stellar populations. Following several billion years of these protracted interactions, the galaxies will ultimately coalesce into a solitary, stable structure. Scientific simulations suggest that the final configuration will not resemble a spiral galaxy like Andromeda or the Milky Way, but rather a colossal elliptical galaxy. This transformation is attributed to the violent nature of the merger process, which randomizes the stellar orbits, thereby obliterating the ordered disk structure characteristic of spiral galaxies. Instead of revolving in a structured manner around a central disk, the stars will traverse more chaotic, three-dimensional trajectories, imbuing the nascent galaxy with an elliptical form. As an elliptical galaxy, it will possess a distinct structure and behavioral pattern compared to its spiral progenitors. The randomized stellar movements that define elliptical galaxies imply that, over time, stars will intermingle more thoroughly than in a meticulously ordered spiral system. Devoid of the continuous rotation that sustains spiral arms, the merged galaxy will evolve towards a more uniform, rounded shape. Its chromatic characteristic will also undergo a shift. Whereas the Milky Way and Andromeda once harbored vibrant regions of stellar formation painted in blue hues, the newly merged entity will gradually adopt a more golden luminescence. This chromatic evolution signifies the maturation of its stellar population, as the brightest and hottest stars exhaust their fuel, leaving behind longer-lived but cooler, reddish stars. Scientists have even bestowed a designation upon this future galactic entity, Andromeda. While it will retain numerous attributes of its parent galaxies, it will also be considerably more substantial, and its central nexus will likely harbor an even more colossal black hole, as the supermassive black holes from both progenitor galaxies progressively spiral towards one another and merge. By the time this grand merger commences, Earth's solar system will have aged by billions of years, and the Sun will have undergone significant evolutionary changes. In approximately 5 billion years, the Sun is projected to expand into a red giant, rendering life on Earth untenable. Nevertheless, should humanity or any other intelligent civilization have successfully navigated survival and achieved interstellar expansion, this galactic merger could present novel opportunities. The influx of gas from Andromeda would provide fuel for stellar genesis, fostering the creation of new, potentially habitable worlds. The redistribution of stars and planetary systems would fundamentally alter cosmic environments, reshaping the structure of interstellar space, and perhaps even facilitating more direct pathways for intergalactic travel. The sheer expanses between stars render direct stellar collisions highly improbable. Consequently, the primary impacts will be gravitational, influencing stellar trajectories and reconfiguring the grand architecture of the galaxy. Certain planetary systems might be propelled into new orbital paths, while others could be expelled entirely. There exists even a minor probability that our solar system could be displaced from its current locus, potentially migrating deeper into the nascent galaxy or being hurled outwards into intergalactic space. Some simulations suggest that following the completion of the merger, Milky will enter a quiescent phase, with most of its chaotic interactions subsiding. Others hypothesize that Milky might subsequently merge with other proximate galaxies, continuing the grand narrative of galactic evolution on an even grander scale. As the universe continues its relentless expansion, the connective forces between galaxies will weaken. The distant galaxies discernible today will recede ever further, their emitted light redshifting into the background tapestry of an ever-expanding cosmos. In the distant future, only the most proximate galaxies, those already merged or gravitationally bound, will remain within observational reach. This implies that long after the initial collision, Milky will stand as an isolated island within an increasingly desolate universe, one of the few remaining colossal galaxies against an ever-darkening celestial canvas. The cosmos is replete with instances of galactic collisions in various stages of evolution, from nascent encounters to fully coalesced elliptical galaxies. By scrutinizing other galaxies currently undergoing mergers, astronomers can juxtapose real-world observations with their computational models, thereby refining their theoretical frameworks and deepening their comprehension of the operative forces. Although humanity will not personally witness this grand cosmic spectacle, our capacity for predictive modeling allows us to glimpse a future epoch where the nocturnal panorama will be radically transformed. A comparative anatomical examination of Andromeda and the Milky Way reveals their shared membership within the local group, a celestial collective comprising over 50 galaxies, prominently featuring these two immense spiral systems. Each boasts billions of stars, expansive arms extending across the cosmos, and supermassive black holes at their central loci. However, their individual developmental trajectories and structural characteristics exhibit variations that shape their present state and prognosticate their future. Andromeda exhibits a greater visible diameter, spanning approximately 220,000 light-years across, in contrast to the Milky Way's estimated 100,000 to 160,000 light-years. Nevertheless, the Milky Way may possess slightly greater mass due to its dense core and an extended halo of dark matter. These disparities prompt inquiries into the mechanisms of galactic growth over cosmic timescales and the factors contributing to their overall mass. Andromeda's expansive disk suggests a history of accreting smaller galaxies, thereby accumulating stars and matter to extend its cosmic reach. Andromeda is estimated to harbor around 1 trillion stars, more than double the number present in the Milky Way, which contains an estimated 200 to 400 billion stars. This quantitative divergence implies that Andromeda has been more prodigious in its star-forming capacity or has undergone mergers with a sufficient number of smaller galaxies to augment its stellar population. However, the aggregate rate of star formation presents a contrasting narrative. Andromeda's star-forming activity has markedly decelerated, whereas the Milky Way continues to exhibit a relatively vigorous production of new stars. The presence of luminous blue clusters and nebulae within the Milky Way's spiral arms is indicative of an ongoing cycle of stellar genesis. While Andromeda appears to be entering a more quiescent phase, Andromeda's central bulge is more substantial and prominent than that of the Milky Way, housing older, redder stars in a tightly packed configuration. This suggests a history marked by significant interactions and mergers that funneled material into its core, catalyzing intense starburst events in the past. The Milky Way's central region, though also densely populated, is less pronounced, suggesting a less tumultuous past or a distinct pattern of stellar migration over cosmic epochs. The black hole situated at the heart of Andromeda, designated M31*, possesses an estimated mass approximately 140 million times that of the Sun. In stark contrast, the Milky Way's Sagittarius A** has a mass roughly 4 million times the Sun's mass. This disparity in magnitude suggests that Andromeda's central region has undergone more profound transformative processes, potentially including the accretion of multiple smaller black holes over time. The presence of a more massive black hole also exerts a discernible influence on the motion of nearby stars, fostering a more dynamic and energetic milieu in proximity to Andromeda's core. Both galaxies exhibit rotational motion, with their spiral arms sweeping through space in a grand celestial choreography. However, Andromeda's rotation is more rapid, with its stars traversing at an average velocity of approximately 250 kilometers per second. By comparison, Milky Way stars move at approximately 220 kilometers per second. This velocity differential may be attributable to variations in mass distribution, with Andromeda's larger stellar population and central bulge contributing to its augmented rotational velocity. Despite these distinctions, both galaxies share fundamental structural characteristics. Each possesses a barred spiral morphology, signifying that their central regions are characterized by elongated stellar bars that channel material inwards, fueling star formation and sustaining their central black holes. These bars are a common feature among spiral galaxies and are believed to develop as a consequence of gravitational interactions over extended periods. Their satellite galaxies also exhibit both similarities and divergences. Both galaxies are encircled by a retinue of smaller companions, including dwarf galaxies and globular clusters. The Milky Way possesses known satellites such as the Large and Small Magellanic Clouds, as well as the Sagittarius Dwarf Galaxy, which is presently undergoing tidal disruption due to gravitational forces. Andromeda's system includes satellites like M32 and M110, which display evidence of past interactions with their parent galaxy. Recent investigations propose that Andromeda's satellites are arrayed in a surprisingly ordered planar configuration, whereas the Milky Way's satellites are more randomly distributed, hinting at divergent formation histories. Infrared revelations illuminate Andromeda in a new perspective. A significant portion of Andromeda's true complexity is obscured by dense clouds of dust that absorb and scatter visible light. This dust acts as a cosmic veil, concealing large swathes of the galaxy and impeding a comprehensive view. Infrared light, however, possesses the capacity to penetrate these obstructions. By observing Andromeda in infrared wavelengths, astronomers can delineate structures and processes that remain imperceptible to conventional optical telescopes. Among the most striking discoveries facilitated by infrared observations is the intricate structure of Andromeda's dust lanes. In visible light, these lanes appear as dark streaks traversing the spiral arms, obscuring the light from stars situated behind them. Yet, in infrared, these very structures emit a radiant glow, revealing elaborate networks of dust that delineate the galaxy's underlying skeletal framework. This dust is an indispensable constituent for stellar formation. Infrared imagery unveils vast reservoirs of cold gas and dust that serve as the primordial material for nascent stars. By examining these regions, astronomers can pinpoint the locations where the next generation of stars will originate, long before they become optically observable. The galactic core is densely packed with stars, and in visible light, their collective brilliance creates a blinding luminescence, rendering it challenging to scrutinize individual stars or structures in close proximity to the center. Infrared telescopes can penetrate this glare, unveiling finer details of Andromeda's nucleus. Encircling the central supermassive black hole is a dense, rotating disk of stars. In visible light, this region presents as a luminous, undifferentiated core. However, in infrared, astronomers can discern the complex kinematics of stars as they orbit under the immense gravitational influence of the black hole. As stars age, they undergo transformations that render them more prominent in infrared wavelengths. Red giant stars, in particular, emit a significant portion of their radiation in the infrared spectrum. By mapping the distribution of these stars, astronomers can reconstruct the long-term evolutionary history of the galaxy. When galaxies collide or interact, they frequently leave behind faint trails of stars, dust, and gas. These tidal remnants and stellar streams can be challenging to detect in visible light, especially when they are spread across immense distances. Infrared surveys, however, can capture the warm luminescence of dust and the faint stellar vestiges left by these past encounters. Another crucial advantage of infrared observations is their capacity to detect low-mass celestial objects that are too dim to be observed in optical wavelengths. Brown dwarfs, sometimes referred to as failed stars, are entities too small to sustain nuclear fusion within their cores. These objects emit the majority of their radiation in the infrared spectrum, rendering them virtually invisible to standard telescopes. Infrared studies have identified populations of brown dwarfs dispersed throughout Andromeda, offering insights into the lower end of the galaxy's stellar constituency. These discoveries contribute to filling the gaps in our understanding of stellar and substellar object formation within a large galaxy. Radio whispers offer unconventional perspectives on Andromeda. While visible and infrared light reveal stars, dust, and thermal energy, radio waves capture a different form of imagery, one shaped by magnetic fields, cold gas clouds, and the faint emanations of cosmic phenomena that have unfolded over millennia. One of the paramount applications of radio astronomy in studying Andromeda lies in mapping its neutral hydrogen content. Neutral hydrogen emits a faint signal at a wavelength of 21 centimeters. This signal, known as the hydrogen line, enables astronomers to trace the distribution of gas throughout Andromeda. By tuning their instruments to this specific wavelength, researchers can generate detailed maps of the galaxy's gaseous structure, indicating potential sites of new star formation and charting the ongoing evolution of Andromeda's spiral arms. Hydrogen observations have revealed that Andromeda's disk extends significantly beyond its optically visible extent. While the luminous portion of the galaxy spans approximately 220,000 light-years, radio maps indicate that its gaseous component extends much farther, merging with the surrounding intergalactic medium. Unlike visible light, which primarily delineates the physical structures of stars and dust, radio signals can be influenced by the presence of magnetic forces. As charged particles spiral along magnetic field lines, they generate synchrotron radiation, a faint yet persistent emission detectable by radio telescopes. By mapping this radiation, astronomers have ascertained that Andromeda possesses an organized magnetic field that pervades a substantial portion of the galaxy. This field plays a role in guiding the trajectories of cosmic rays and influences the dynamics of interstellar gas, thereby impacting the location and manner of star formation. Another discovery made through radio astronomy is the presence of pulsars within Andromeda. As pulsars rotate, their emitted beams sweep across space, producing rhythmic pulses detectable from Earth. Despite Andromeda's distance of millions of light-years, sensitive radio telescopes have identified several pulsars within the galaxy, providing novel insights into the terminal stages of stellar evolution in a system beyond our own. Andromeda's central region also emits intriguing radio signals. M31*, while not exhibiting the same level of activity as the supermassive black holes found in some other galaxies, still emanates a faint radio glow. This radiation originates from charged particles spiraling within the intense magnetic fields proximate to the black hole. Radio waves afford astronomers the capability to directly probe this turbulent environment. By examining these emissions, researchers can glean further knowledge regarding the feeding mechanisms of the black hole and its interactions with the surrounding milieu. Beyond the central black hole, Andromeda harbors enigmatic sources of radio waves that lack clear counterparts in optical or infrared imagery. Some of these sources may represent the remnants of ancient supernova explosions, where expanding shock waves have energized surrounding material, causing it to emit radiation at radio wavelengths. Others might be regions of vigorous star formation, where young, massive stars are ionizing the ambient gas and triggering bursts of radio emission. The identification and comprehension of these sources remain an ongoing scientific challenge, necessitating continuous observation with increasingly sensitive instruments. Radio astronomy has also proven instrumental in the search for signals that might indicate the presence of intelligent life. Although no evidence has been found to date, some astronomers have directed radio telescopes towards Andromeda in the hope of detecting artificial signals, structured patterns that deviate from the random noise inherent in natural cosmic processes. These searches, conducted as part of the broader endeavor known as the Search for Extraterrestrial Intelligence, SETI, are predicated on the assumption that if intelligent civilizations exist within Andromeda, they might employ radio waves for communication, much like humanity. The forthcoming square-kilometer array telescope will possess the capability to map the galaxy's magnetic field with even greater resolution, detect fainter hydrogen signals, and uncover novel sources of radio waves that have thus far remained undetected. Through radio astronomy, Andromeda imparts its secrets across the vast expanse of space, offering clues to astronomers who are attuned to its subtle whispers. Gravitational lensing. Andromeda as a cosmic lens. One of the most valuable applications of gravitational lensing is its capacity to unveil hidden galaxies from the early universe. By magnifying the light emanating from distant objects, Andromeda functions as a natural telescope, enabling astronomers to peer billions of years into the past. These magnified galaxies, observed as they existed in a much younger universe, provide critical data regarding the formation of the first stars and galaxies. Without the gravitational influence of Andromeda, these remote cosmic structures would be virtually imperceptible, even with the most powerful telescopes. A challenge in detecting gravitational lensing within Andromeda stems from the presence of its own stars, gas, and dust. Given the galaxy's relative proximity to Earth, its bright features can obscure the much fainter background galaxies being lensed. However, astronomers have devised sophisticated techniques to filter out foreground noise, allowing them to focus on the gravitational distortions induced by Andromeda's mass. These methodologies involve meticulous analysis of how light is stretched and amplified across various regions of the galaxy, revealing patterns indicative of lensing effects. Beyond the study of distant galaxies, gravitational lensing can also be employed to detect objects closer to home. In infrequent instances, individual stars within Andromeda can act as diminutive lenses, magnifying the light from even more distant stars in the background. This phenomenon, known as microlensing, occurs when a star's gravitational field temporarily bends and brightens the light of another star situated directly behind it. These transient bursts of enhanced vision can reveal vital clues about the distribution of invisible entities, such as rogue celestial bodies, black holes, and even nebulous aggregations of dark matter traversing the cosmos. Gravitational microlensing has already served its purpose in discovering worlds beyond our solar neighborhood. Furthermore, celestial cartographers are hopeful that by employing the same methodology within the Andromeda Galaxy, they might one day pinpoint alien planets that orbit stars in that far-off stellar congregation. Although a daunting endeavor, such a revelation would signify a profound advancement in the quest for exoplanets beyond the Milky Way. The capacity to identify planetary arrangements in Andromeda via gravitational lensing would furnish an entirely novel avenue for scrutinizing the formation and evolution of planets within diverse galactic settings. Researchers are also exploring the potential for Andromeda's gravitational lensing to validate fundamental tenets of physics. Light traversing a gravitational field does not merely bend, it also experiences temporal discrepancies. When multiple images of a background galaxy or quasar emerge due to lensing, the light from each image follows a distinct trajectory through space. Should the background source exhibit variability, such as an intermittent quasar, astronomers can precisely measure the minute disparities in arrival times between each gravitationally distorted image. This temporal lag can yield significant insights into the rate at which the universe is expanding, and even aid in refining estimations of the Hubble constant, the numerical value that quantifies the universe's growth. Cosmic thoroughfares, hypothetical spacetime tunnels, and intergalactic shortcuts. The concept of wormholes finds its origins in Einstein's theory of general relativity. This theoretical framework proposes that spacetime can be contorted and warped by massive objects, and in certain theoretical constructs, it could be so distorted that two widely separated points become directly linked by a concealed passage. This conduit, often referred to as an Einstein-Rosen bridge, would function akin to a tunnel through the fabric of spacetime, facilitating instantaneous transit between its two extremities. Should a stable wormhole exist connecting the Milky Way and Andromeda, it would obviate the necessity for conventional propulsion systems, enabling virtually instantaneous travel between the two galaxies. In accordance with general relativity, a wormhole would, by its very nature, collapse almost immediately after its inception. To counteract this inherent instability, scientists posit the requirement of an unusual form of matter possessing negative energy density, a substance yet to be discovered, to maintain the aperture open. This exotic matter would exert an outward pressure against the wormhole's boundaries, preventing their collapse and permitting passage. The investigation for wormholes has predominantly been pursued through indirect observational evidence. Certain researchers have proposed searching for their gravitational influence, analogous to how black holes are detected. If a wormhole were to exist, light passing in its vicinity might be distorted in a manner that deviates from the behavior observed with a typical gravitational lens. Some theories even suggest that certain black holes might actually serve as gateways to wormholes, though this remains purely speculative. Observations of Sagittarius A*, the supermassive black hole at the center of our galaxy, have not yielded any corroborating evidence for such a structure, yet the pursuit continues. Beyond the question of their existence lies another significant challenge: how they might be traversed. If a wormhole were to connect the Milky Way and Andromeda, an entry point would still be necessary. Theoretically, a spacecraft approaching a stable wormhole would encounter immense gravitational forces at its mouth. If the entrance were surrounded by intense energetic radiation or an event horizon, reaching it might prove impossible. Even if a vessel could breach the threshold, the internal passage of the tunnel might not be smooth or direct. Some theoretical models propose that a traveler could be unpredictably stretched or compressed within the wormhole, rendering safe passage highly improbable. An additional complication pertains to the potential consequences of time dilation. Within the framework of Einstein's relativity, the passage of time is variable, influenced by velocity and gravitational fields. If a wormhole were to link two distant points in spacetime, it might also connect two different moments in time. This possibility raises profound questions regarding causality and the potential for paradoxes. In certain hypothetical scenarios, traversing a wormhole could permit an individual to arrive at their destination prior to their departure, thereby creating logical inconsistencies that current physics has yet to fully resolve. If wormholes could be utilized in this manner, they might not only function as cosmic transit routes, but also as potential temporal displacement devices, adding another layer of enigma to their theoretical existence. Alternative theoretical constructs have also been proposed that could offer analogous shortcuts across the vastness of the cosmos. One such concept involves cosmic strings, exceedingly slender, high-energy filaments that may have originated in the nascent universe. Certain theories suggest that if two cosmic strings were to pass each other at considerable velocities, they could warp spacetime in a manner that facilitates shortcuts between distant locations. These hypothetical structures, if they indeed exist, could present an alternative to the conventional wormhole paradigm by creating natural pathways through spacetime. Some researchers have explored the notion that minuscule wormholes might exist at the quantum level, continuously forming and dissipating as an intrinsic aspect of spacetime's fundamental architecture. If this hypothesis holds true, some speculate that an advanced civilization might eventually acquire the capability to stabilize and enlarge these quantum wormholes, thereby forging traversable passages between galaxies. This remains a concept far beyond our present technological comprehension, yet it underscores the latent possibilities inherent in the very fabric of the universe. Should a civilization attain the capacity to harness immense quantities of energy, vastly exceeding anything currently achievable, it might be empowered to directly manipulate spacetime. Theoretical models suggest that if negative energy could be generated and controlled, an artificial wormhole could be engineered and stabilized. If spacetime shortcuts exist, could the cosmos be interconnected in ways that currently elude our understanding? Some theoretical frameworks propose that our universe might be an integral component of an extensive network of spacetime conduits, with galaxies and even entire universes linked by concealed pathways. Despite the prevailing uncertainties surrounding wormholes, their theoretical investigation continues to be a significant pursuit within theoretical physics. Even if they are never empirically detected or artificially created, the endeavor to comprehend them has, over time, yielded profound insights into the nature of gravity, spacetime, and the fundamental characteristics of the universe. Extragalactic habitability within Andromeda. The fundamental prerequisites for life, as we understand it, remain constant, irrespective of its location. A planet must maintain a stable orbital path around its parent star, be situated within the circumstellar habitable zone where liquid water can exist, and possess an atmosphere capable of sustaining complex chemical processes. These factors are relatively well understood when investigating exoplanets within our own Milky Way galaxy. However, when applied to Andromeda, they introduce novel layers of complexity. The sheer immensity of the distance to Andromeda renders direct observation of individual planets virtually impossible. Nevertheless, by meticulously analyzing Andromeda's structural composition, its stellar demographics, and prevailing theories of planetary formation, researchers can formulate informed hypotheses regarding the environments most conducive to the emergence of life. One of the primary indicators of potential habitability is the distribution of stars rich in heavy elements. Planets capable of supporting life necessitate the presence of elements heavier than hydrogen and helium, such as carbon, oxygen, and nitrogen, for the formation of atmospheres and biological molecules. These elements are synthesized within stars and subsequently dispersed through supernova events. Andromeda exhibits a well-intermingled population of both young and ancient stars. The younger stellar generations signify an ongoing process of planetary formation, mirroring that observed in the Milky Way, thereby increasing the probability that rocky planets exist within habitable zones. Andromeda's history of galactic mergers and interactions with smaller galaxies has profoundly shaped its current configuration. Such celestial collisions can destabilize planetary systems by altering stellar orbits, initiating intense bursts of radiation, or even ejecting planets into interstellar space. While Andromeda has largely stabilized following its past encounters, regions in close proximity to its galactic nucleus or areas characterized by high stellar density may be too dynamically chaotic to support stable planetary systems over billions of years. Conversely, the outer spiral arms might offer more quiescent environments where planets could maintain predictable orbits for sufficient durations to allow for the evolution of life. Within our own galaxy, water-bearing exoplanets have been identified, alongside icy moons that potentially harbor subsurface oceans. The existence of these icy moons suggests that life might not be exclusively confined to planets situated within the habitable zone of their stars. Instead, it could potentially arise on moons orbiting gas giants, shielded beneath substantial ice layers where internal geothermal activity prevents complete water solidification. The significant challenge lies in the fact that detecting water within Andromeda's planetary systems is considerably more arduous than within the Milky Way. At Andromeda's immense distance, resolving individual stars with the requisite level of detail is currently beyond the scope of our technological capabilities. Some scientists have posited the possibility of silicon-based life forms, which could potentially thrive in environments inimical to Earth-like organisms. Andromeda encompasses a diverse array of stellar types, ranging from diminutive red dwarfs to colossal blue giants. Consequently, the planets orbiting these stars may experience a wide spectrum of extreme environmental conditions. Planets possessing dense atmospheres composed of ammonia or methane could potentially host entirely distinct biochemical processes, thereby expanding the potential scope of habitability beyond that considered typical for Earth-like life. Within the Milky Way, astronomers actively seek biosignatures, chemical indicators that suggest the presence of life, such as oxygen, methane, and carbon dioxide in the atmospheres of exoplanets. The detection of such gases in Andromeda would be markedly more challenging due to the inherent limitations of current telescopic technology. Nevertheless, future generations of scientists might be able to analyze the atmospheres of distant exoplanets, searching for the telltale indications of biological activity. Some researchers propose searching for planetary atmospheres that exhibit an apparent imbalance, where the coexistence of gases like oxygen and methane implies ongoing biological processes. The identification of a planet with an anomalous atmospheric composition could serve as a strong hint of life, even if the specific details remain elusive. Should an advanced civilization exist within Andromeda, it might leave detectable traces of its technological presence. Some astronomers have suggested searching for artificial signals, akin to the SETI initiatives within our own galaxy. A sufficiently advanced civilization could employ radio waves, laser pulses, or even colossal energy harvesting structures such as Dyson spheres to capture and utilize stellar energy. If such megastructures were present in Andromeda, they might generate infrared signatures detectable by sensitive instruments. However, the search for extraterrestrial intelligence encounters numerous obstacles, including the sheer immensity of Andromeda and the inherent unpredictability of alien technological capabilities. Civilizations might employ communication methodologies entirely foreign to human understanding, rendering their detection even more elusive. The advanced age of Andromeda also presents an intriguing consideration. It has been a cradle for star formation for billions of years, implying that if intelligent life emerged early in its history, it could be significantly more advanced than humanity, or it may have long since ceased to exist. The Andromeda Protocol, a conceptual framework for future extraterrestrial colonization. Should humanity ever contemplate the endeavor of colonizing the Andromeda Galaxy, such an undertaking would necessitate a meticulously structured and methodical strategy. A mission of this magnitude would be unprecedented, demanding cutting-edge technology, long-range strategic planning, and a profound understanding of interstellar survival. The Andromeda Protocol, a theoretical blueprint for humanity's expansion beyond the Milky Way, would serve as a guiding framework for such an ambitious undertaking. It would delineate the requisite developmental stages, commencing with initial exploratory voyages and culminating in the establishment of self-sufficient colonies in a distant galaxy. The initial phase of any serious attempt to reach Andromeda would involve the development of intergalactic propulsion systems capable of traversing the immense distances separating galaxies. Achieving practical intergalactic travel would likely necessitate groundbreaking advancements in propulsion technologies, such as antimatter engines or theoretical concepts like the Alcubierre warp drive. Prior to any large-scale human presence in Andromeda, the initial phase of the protocol would likely entail the deployment of robotic probes. These autonomous explorers would be engineered to gather critical data concerning Andromeda's planetary systems, star clusters, and potential hazards. Unlike current probes that rely on radio signals taking minutes or hours to reach Earth, intergalactic probes would require sophisticated artificial intelligence for autonomous decision-making. They would identify potentially habitable worlds, map resource distribution, and transmit data back to the Milky Way via advanced communication systems, possibly leveraging quantum entanglement or other speculative methodologies. Once a suitable target within Andromeda has been identified, the subsequent phase would involve dispatching self-replicating robotic fabrication units to establish essential infrastructure before the arrival of human settlers. These systems, equipped with nanotechnology and advanced 3D printing capabilities, could extract raw materials from asteroids or planetary surfaces, constructing vital structures such as orbital stations, human habitats, and energy collection arrays. Automated terraforming efforts could commence on selected planets, modifying their atmospheres to render them more conducive to human habitation. The utilization of bioengineered organisms, such as microbes capable of oxygen production, could play a role in shaping planetary environments long before the first colonists set foot on alien soil. The method of transporting human settlers to Andromeda would represent one of the most complex challenges within the protocol. The journey could span an unfathomable number of years unless faster-than-light travel is achieved, necessitating the existence of multi-generational starfaring civilizations aboard colossal starships. These vessels, sometimes referred to as world ships, would be self-sustaining, encompassing entire ecosystems, manufacturing facilities, and living quarters for populations that might never physically inhabit a planetary surface. Generations of crews would live and perish aboard these ships, diligently preserving knowledge and adapting to an existence detached from Earth. If human cryosleep becomes a viable option, passengers could remain in a state of profound unconsciousness for centuries, awakening only upon arrival in Andromeda. Alternatively, the concept of mind uploading, wherein human consciousness is transferred into artificial substrates, could enable settlers to be transmitted digitally, stored within advanced artificial intelligence networks, and subsequently instantiated in physical forms through robotic avatars or bioengineered clones upon reaching their destination. Upon arrival in Andromeda, establishing a secure foothold would require meticulous strategic planning. The initial human outposts might take the form of orbital habitats, expansive space stations situated in proximity to resource-rich planetary systems. These stations would serve as operational hubs, overseeing planetary exploration and surface expeditions. They would also function as vital waypoints for subsequent arrivals, thereby creating a network of interconnected settlements throughout Andromeda. Terraforming initiatives could continue concurrently, ensuring long-term habitability for future generations. One of the most critical components of the Andromeda Protocol would be the establishment of self-sustaining ecosystems. Unlike Earth, whose biosphere evolved over billions of years, a new colony would need to construct its life support environment from the ground up. Genetically engineered food sources and artificial biospheres could provide sustenance in environments where natural agriculture is unfeasible. A settlement in Andromeda would be geographically isolated from Earth for millennia, if not permanently, rendering real-time communication impossible. The emergence of independent societies, shaped by their unique environmental conditions and technological capabilities, could lead to the development of entirely novel cultural and political systems, distinct from anything found on Earth. Should Andromeda harbor intelligent civilizations, any human expansion would need to carefully consider the ethical and practical ramifications of contact. The Andromeda Protocol would likely incorporate guidelines for first contact scenarios, ensuring that interactions are conducted with utmost caution and respect. If another civilization already claims dominion over portions of Andromeda, humanity might need to negotiate a framework for coexistence or risk engaging in conflict on an intergalactic scale. Defensive strategies would also need to be formulated to guard against both natural cosmic hazards and potential hostile entities. Asteroids, gamma-ray bursts, and rogue black holes pose significant threats to any settlement, demanding constant surveillance and rapid response capabilities. If Andromeda is indeed home to advanced extraterrestrial civilizations, humanity's expansion efforts would necessitate astute diplomatic and strategic planning to avert unintentional aggression or territorial disputes. Notwithstanding the formidable challenges, the colonization of Andromeda would represent a monumental leap in the evolutionary trajectory of humankind. It would transform us from a species confined to a single galaxy into an intergalactic civilization capable of thriving across cosmic distances. Such a journey would not only test the outer limits of human ingenuity and resilience, but would also fundamentally redefine the very nature of life, bridging the chasm between what is currently achievable and what lies beyond the realm of imagination. Technological frontiers, novel instruments for extragalactic astronomy. One of the most significant advancements in contemporary astronomy involves the enhancement of large optical telescopes. These sophisticated instruments gather light from distant celestial objects, thereby producing detailed visual representations of galaxies such as Andromeda. The latest generation of ground-based telescopes, including the Extremely Large Telescope, ELT, located in Chile, are engineered to capture imagery with unparalleled clarity. With a primary mirror exceeding 30 meters in diameter, the ELT will possess the capability to detect faint objects with a precision previously unattainable. Adaptive optics, a transformative technology that actively corrects for image distortions caused by Earth's atmosphere, further refines these observations by continuously adjusting mirror surfaces to compensate for atmospheric turbulence. Modern telescopes can now achieve image sharpness comparable to those acquired from orbital platforms. Space-based telescopes offer an even more pristine view, entirely unhindered by atmospheric interference. The Hubble Space Telescope has played an instrumental role in the study of Andromeda, capturing awe-inspiring images that reveal its intricate structure with remarkable detail. More recently, the James Webb Space Telescope, JWST, has elevated this observational capability to new heights. Designed for infrared spectrum observation, the JWST can penetrate cosmic dust clouds, unveiling stars, and planetary systems that were previously obscured. By analyzing infrared emissions, astronomers can study cooler celestial bodies such as distant planets, nascent star-forming regions, and ancient galaxies. In the context of Andromeda, the JWST has provided novel insights into its stellar populations and the dynamics of gas movement within the galaxy. The Square-Kilometre Array, an impending network of radio telescopes, is poised to become one of the most powerful instruments for investigating extragalactic structures. It will assist scientists in tracking the temporal evolution of Andromeda's stars and interstellar material. In contrast to optical telescopes, radio observatories can function effectively even under cloudy conditions or during daylight hours, enabling continuous monitoring of astronomical phenomena. Spectroscopic instruments function by deconstructing light into its constituent wavelengths, akin to how a prism creates a rainbow. This analytical technique empowers astronomers to ascertain the chemical composition, temperature, and motion of stars and gaseous nebulae within a galaxy. The KK Observatory, for instance, employs advanced spectrographs to analyze the light emanating from Andromeda's galactic core, precisely measuring the velocity of its stars and confirming the presence of its central supermassive black hole. The application of spectroscopy has been instrumental in discerning distinct epochs of stellar birth, illuminating the developmental trajectory of Andromeda's star population. The European Space Agency's Gaia Space Observatory has profoundly transformed our understanding of our own galaxy by furnishing precise measurements of the positions and movements of over 1 billion stars. A comparable methodology is now being employed for Andromeda, enabling astronomers to construct a dynamic representation of its structure. By meticulously tracking the trajectories of individual stars, researchers can reconstruct prior galactic encounters, identify stellar clusters originating from assimilated galaxies, and forecast Andromeda's future evolution. Extensive astronomical surveys, such as those conducted by the Vera C. Rubin Observatory, generate imagery of millions of galaxies, necessitating sophisticated computational tools for pattern analysis and the detection of subtle celestial formations. Artificial intelligence algorithms excel at pinpointing anomalies, categorizing various galaxy types, and even anticipating future galactic mergers. Within the context of Andromeda, machine learning is proving invaluable in revealing faint tidal streams. Gravitational wave observatories, including LIGO and Virgo, have successfully detected distortions in spacetime resulting from the coalescence of black holes and neutron stars. Anticipated future gravitational wave observatories, such as the proposed Laser Interferometer Space Antenna, LISA, are poised to detect signals emanating from supermassive black holes situated at galactic centers. Should Andromeda's M31 stellar mass black hole merge with another substantial black hole, it would generate detectable gravitational waves, thereby offering a novel avenue for studying galactic interactions. Another promising technique is neutrino astronomy, which involves the detection of nearly massless particles that traverse matter with remarkable ease. Neutrinos are generated in extreme cosmic environments, such as the hearts of supernovae or the vicinity of black holes. The IceCube Neutrino Observatory in Antarctica has already registered high-energy neutrinos originating from distant galaxies. With advancements in detector sensitivity, future instruments may unveil concealed activity within Andromeda's core. The ongoing enhancement of space-based telescopes will further augment humanity's capacity to investigate Andromeda and other remote galaxies. Future observatories, conceptualized as the Habitable Worlds Observatory and the Large UV Optical Infrared Surveyor, LUVOIR, are expected to provide even sharper imagery and more profound observational data. These next-generation instruments will be instrumental in the search for exoplanets, the examination of galaxy formation, and the identification of evidence for life beyond the Milky Way. Emerging theories, unresolved questions, and new frontiers beckon. One of the most significant enigmas pertains to Andromeda's distribution of dark matter. Analogous to the Milky Way, Andromeda appears to be enveloped by an enigmatic halo of dark matter. Observations of Andromeda's satellite galaxies suggest that this dark matter halo may exhibit greater heterogeneity than initially presumed. Certain regions appear to possess a higher concentration of dark matter than others, raising questions regarding its distribution and the potential need to revise our current understanding of dark matter. Andromeda exhibits a complex arrangement of spiral arms, but their behavior deviates from that observed in the Milky Way. Some research indicates that a past galactic interaction may have sculpted these structures, while alternative theories propose that internal galactic disk processes were responsible for their formation. Observational data from telescopes, such as the Hubble Space Telescope and the forthcoming Nancy Grace Roman Space Telescope, aim to generate more detailed maps of Andromeda's spiral arms, potentially elucidating their evolutionary history over billions of years. The exceptionally large number of globular clusters in Andromeda presents another ongoing puzzle. Andromeda hosts over 500 known globular clusters, more than double the count in the Milky Way. Some researchers posit that Andromeda's globular clusters represent remnants of ancient dwarf galaxies that were assimilated over time. Others suggest that Andromeda has demonstrated an unusual proficiency in forming such clusters. Studying their spatial distribution and chemical composition could provide insights into the galaxy's past and the mechanisms by which it accumulated its stellar population. The central region of Andromeda harbors another enigma: its supermassive black hole. This black hole is considerably more massive than its counterpart at the Milky Way's core. Despite the similar overall sizes of the two galaxies, scientists have yet to ascertain the reason for Andromeda's black hole's exceptional mass or its influence on the surrounding cosmic environment. Future observations utilizing radio telescopes and X-ray observatories may shed light on this mystery by examining the matter accreting onto the black hole and the high-energy radiation it emits. The question of whether Andromeda has already commenced interacting with the Milky Way remains an active area of research. Although the two galaxies are not predicted to fully collide for billions of years, some astronomers believe that their surrounding halos of gas and dark matter may already be overlapping. If this is the case, it could signify that the initial stages of their eventual merger are already in progress. Future space telescopes will be capable of more closely analyzing the movement of intergalactic gas, searching for evidence of interaction that could substantiate or refute this hypothesis. Recent studies suggest that Andromeda may have undergone periods of intense star formation in its past, followed by intervals of relative quiescence. Some models propose that these bursts were precipitated by prior galactic encounters, while others suggest they could be attributable to internal processes. Mapping the ages and elemental compositions of stars across Andromeda's disk and halo could contribute to assembling a more coherent timeline of its formation. Galaxies are not isolated entities. They exist within a vast cosmic architecture comprised of filaments, voids, and clusters. Some researchers contend that Andromeda and the Milky Way are constituents of a larger formation known as the local sheet, a flattened arrangement of galaxies extending for millions of light-years. Examining Andromeda's motion and position within this structure could reveal fundamental principles governing galaxy formation and movement in the broader universe. Certain astronomers have proposed that studying Andromeda's rotational patterns and mass distribution might offer clues regarding the completeness of our current understanding of gravity. Alternative theoretical frameworks, such as modifications to Newtonian dynamics, seek to explain specific galactic behaviors without invoking the concept of dark matter. If observations of Andromeda reveal discrepancies with prevailing models, it could stimulate renewed discussions concerning the fundamental nature of gravity itself. Alien architectures, megastructures within the Andromeda Galaxy. Should an advanced extraterrestrial civilization exist within the Andromeda Galaxy, its influence on the cosmos could potentially be discernible even from our remote vantage point. Megastructures, colossal artificial constructions engineered on a scale far surpassing human capabilities, represent one of the most captivating possibilities in the quest for extraterrestrial intelligence. These engineered marvels could reconfigure entire star systems, redirect energy on a galactic scale, or even manipulate spacetime itself. While definitive evidence of such structures has yet to be found, scientists continue to scrutinize Andromeda with this prospect in mind, employing observational techniques that might detect the telltale signs of alien engineering. One of the most widely debated forms of megastructure is the Dyson sphere, a theoretical construct envisioned for capturing and harnessing the energy output of a star. First conceptualized by physicist Freeman Dyson, such a structure could manifest in various configurations. A complete Dyson sphere would entirely encompass a star, absorbing nearly all of its radiated light. In contrast, A Dyson swarm or Dyson ring would comprise numerous smaller orbiting satellites designed to collect energy. If such structures were present in Andromeda, they might be detectable by identifying stars that appear dimmer than expected in visible light, but emit an excess of infrared radiation due to waste heat. Extensive surveys utilizing infrared telescopes, such as NASA's Wide Field Infrared Survey Explorer, WISE, have scrutinized Andromeda's vast stellar population for anomalies that could indicate large-scale energy harvesting. Although no unequivocal evidence of a Dyson sphere has been discovered, researchers remain open to the possibility that future missions equipped with more sensitive instruments might detect such formations. The discovery of a Dyson sphere or a comparable construct built by an alien civilization would signify an extraordinary level of technological advancement, potentially placing such a civilization among the most sophisticated in the universe. Beyond Dyson spheres, other hypothetical megastructures could exist within Andromeda, each serving a distinct purpose. A stellar engine, for instance, is a theoretical device designed to propel an entire star system by directing its energy output in a specific vector. One proposed design, the Chicago thruster, involves the construction of a massive mirror that reflects a star's radiation asymmetrically, thereby gradually nudging the star in a desired direction. If such a structure were operational in Andromeda, it might be betrayed by the anomalous motion of a star or a group of stars exhibiting drift patterns inconsistent with natural gravitational forces. Another possibility is the existence of artificial ring worlds, immense structures encircling a star at an orbital distance comparable to that of a habitable planet. Unlike a Dyson sphere, a ring world would not fully enclose the star but would instead provide an expansive habitable surface along its inner circumference. Such a construct could offer substantially more living space than a natural planet, and might be detectable by its peculiar light curve, as it would periodically occlude a portion of its star's light when observed from Earth. If an advanced species in Andromeda has engineered such structures, their identification would challenge prevailing assumptions regarding the limits of engineering and planetary habitability. Some researchers have speculated about even more ambitious megastructures capable of reconfiguring entire galactic sectors. A Matryoshka brain, for example, is a theoretical construct comprising multiple concentric layers of Dyson-like energy collectors, designed not only for power generation, but also for advanced computational purposes, effectively creating a superintelligent artificial mind on a colossal scale. If an advanced civilization in Andromeda has developed such a system, it might manipulate its environment in ways detectable from Earth. Anomalous electromagnetic emissions, artificial radiation pulses, or inexplicable patterns in stellar motion could potentially signal the presence of such an intelligence. Galactic-scale engineering might extend even further. Some theorists have posited the possibility of manipulating black holes, either for energy production or for the creation of artificial wormholes, to facilitate faster-than-light travel. If such a civilization exists in Andromeda, its activities might be discernible through abnormal black hole behavior, perhaps unusual fluctuations in X-ray emissions or directed energy jets deviating from typical natural patterns. The concept of civilizations harnessing the power of black holes is speculative, yet it raises intriguing questions about life's potential to shape the cosmos on immense scales. Another approach to searching for evidence of alien megastructures in Andromeda involves identifying objects that defy natural explanations. Large-scale radio surveys have already detected anomalous signals from various cosmic regions, though none have been definitively identified as artificial. Some researchers suggest that directed energy transmissions, potentially signals used for interstellar communication or power distribution, could be detectable with sensitive radio telescopes. If Andromeda hosts an advanced civilization, it is conceivable that it has established a network of artificial signals that might one day be intercepted by human instruments. Certain scientists hypothesize that a highly advanced civilization might leave behind subtle signatures rather than overtly conspicuous structures. Instead of massive physical constructions, they might employ advanced nanotechnology or even manipulate the very fabric of space-time. If an alien species in Andromeda possesses technology far beyond human comprehension, its presence might only be detectable through its indirect effects on natural cosmic phenomena. Deviations from expected stellar behavior or unexplained fluctuations in the cosmic microwave background radiation could potentially indicate the influence of an advanced intelligence. Should a megastructure ever be discovered in Andromeda, it would represent one of the most significant scientific breakthroughs in history. It would serve as definitive proof that intelligent life is not only feasible, but also capable of reconfiguring the universe in extraordinary ways. Such a finding would compel humanity to reevaluate its position within the cosmos, offering a glimpse into the potential achievements of civilizations far older and more advanced than our own. Even in the absence of discovered megastructures, the search itself enhances our comprehension of Andromeda and the broader universe, pushing the boundaries of current knowledge and inspiring future generations to continue exploring the cosmos's mysteries. Cosmic rebirth. The reemergence of life following galactic collisions. Galactic collisions are frequently envisioned as catastrophic events, resulting in stars being ejected from their orbits, entire systems being displaced, and the gravitational forces of merging entities reshaping the cosmic landscape. However, within this apparent chaos lie new opportunities. The violent interaction between Andromeda and the Milky Way will not only dismantle existing structures, but also create environments where conditions conducive to life may arise anew. This is a process of transformation rather than absolute obliteration, wherein the fundamental constituents for new worlds are reorganized, igniting the potential for life to flourish in unexpected locations. As the two galaxies converge, vast nebulae of gas will undergo compression. This compression initiates an intense phase of star formation, often referred to as a starburst. These newly formed stars will be encircled by swirling disks of dust and gas, the primordial material for planetary systems. Some of these stars may form within stable regions where planets with life-supporting conditions could eventually coalesce. Others may acquire worlds that have survived the cosmic upheaval, perhaps altered but still retaining the potential for habitability. If life already exists within one of these systems, it might endure the transition, adapting to its modified surroundings. New planetary systems originating in the aftermath of a galactic collision will be subjected to extreme conditions. Radiation levels will be elevated due to the prevalence of young, hot stars emitting powerful stellar winds and intense ultraviolet radiation. Nevertheless, this does not necessarily preclude the establishment of life. Some of Earth's most resilient organisms thrive in extreme environments, ranging from deep-sea hydrothermal vents to radiation-saturated landscapes. If analogous conditions prevail on newly formed planets, primitive life forms might emerge and persist, shielded by dense atmospheres, subterranean reservoirs, or extensive subsurface oceans. The gravitational turbulence of a galactic merger will also dislodge entire planets from their host stars, sending them adrift as rogue worlds into the void. Although these planets would lack the warmth of a nearby sun, they might still retain internal heat generated by radioactive decay or tidal forces. If they possess substantial atmospheres or subsurface oceans insulated by ice layers, they could sustain life even in the absence of a central star. The collision between Andromeda and the Milky Way could scatter these rogue planets throughout the newly merged galaxy, potentially carrying microbial life on a journey through the desolate expanse of interstellar space. The immense forces involved will eject clouds of gas, dust, and organic molecules into novel regions. These organic compounds, including amino acids, complex hydrocarbons, and other precursors to life, will be dispersed across the galactic environment. If they alight on newly forming planets or moons under suitable conditions, they could catalyze the development of biological processes. Some scientists theorize that life on Earth may have originated from such cosmic chemistry delivered by comets or asteroids rich in organic material. A galactic merger, with its widespread redistribution of matter, could amplify this process on a much grander scale. The Milky Way currently possesses a region designated as the Galactic Habitable Zone, a band where conditions are neither excessively chaotic nor too barren for life to develop. Following the merger, this habitable zone might shift as new star-forming regions emerge and older, more stable systems relocate. Certain areas that were once inhospitable might find themselves situated in more tranquil environments where life has a greater probability of flourishing. Conversely, regions that previously supported stable planetary systems could be disrupted, propelling potentially life-bearing worlds into more hostile conditions. Some planetary systems will remain relatively unaffected by the ensuing chaos, continuing their orbits around their host stars as they have always done. If life exists on any of these worlds prior to the merger, it may survive the transition. Intelligent civilizations, if present, might face considerable challenges in adapting to the evolving galactic environment. However, they might also benefit from new opportunities. A galactic merger could expose advanced species to novel regions of space, potentially accelerating exploration, discovery, and even interstellar migration. Civilizations on the verge of collapse in one galactic sector might find refuge in another, borne along by the shifting cosmic currents. From devastation emerges renewal. The violent ballet of two merging galaxies will disperse ancient stars, forge new ones, and reconfigure the structure of space on an immense scale. Yet, amidst this cataclysm, life may find a pathway to renewal. Whether it emerges on newly formed planets, perseveres in secluded havens, or journeys between the stars on fragments of shattered worlds, the narrative of life within Andromeda and the Milky Way is far from concluded. The galaxy resulting from their union will be characterized by change, adaptation, and perhaps rebirth. And with that thought-provoking note, our exploration concludes. Please share your thoughts on what captivates you about Andromeda in the comments below. If you enjoyed this celestial journey, consider leaving a like and subscribing to our channel. Thank you for watching.